So our first set of presenters, by the way, are the UAPx team. We have with us Dr. Kevin Knuth. Dr. Kevin Knuth is a professor of physics at the University of Albany. And he joined us in 2019, gave an excellent presentation to us on relativistic interstellar travel, which was fascinating. In the context that he was able to show how objects were basically moving at speeds that would be equivalent to interstellar craft. And that was fascinating to hear. And we also have back with us Dr. Matthew Shadegas, who had talked a lot about, he was on a panel that first year. Last year he was on talking about dark matter and dark energy and the relationship that it might have to UFOs and UAPs. So that was quite interesting, and we look forward to hearing what they have. In addition to that, we have Mr. Christopher Altman, who is going to be joining us virtually, who is a part of that team, and I'm looking forward to having him as well. He's got a very healthy background. If you take a look at the materials I gave you and posted online, you can see he's been all over the board in terms of his research. And I'm proud to have him coming in. He's from, I believe he might be coming from Hawaii, if I remember correctly. No, not Hawaii. Where is it? Philippines. I seem like I've seen him all over the place. But anyway, I'm thrilled to have him on board as well, and I hope you'll be pleased. So I'm going to turn that over to these gentlemen.
All right, great. Thank you for having us here, and thank you for this excellent organization, Richard. This is wonderful. And it's very good to be here, and I'm here with Matthew Shadegas, and Christopher Altman will be online, and we're going to talk about some of our initial preliminary results from UAPx. Well, initial preliminary, that sounds a little redundant. Think of initial as being an adverb modifying preliminary, right? So one of the difficulties is that we've collected, last year we collected over 900 hours of infrared video from multiple cameras, about eight infrared FLIR cameras. And this takes a huge amount of time to go through. Analyzing any data takes a lot of work. And when you've got 900 hours of video, it's rather daunting. And one of the basic tenets of UAPx is that we are working to be fully transparent, because we don't see this in the UFO community. There are other groups out there collecting data and have been collecting data that still aren't transparent, and that's a problem. And so we're working on being transparent, and I know that people have been anxious to see what we've had, or what we've recorded. We're anxious to see what we've recorded, and so we are presenting some initial preliminary results. I wish I had something more definitive to say, but in some ways this is a bit risky, because we haven't gone through everything yet. We don't know what we've observed, and we haven't ruled out all of the prosaic explanations yet. So we are putting ourselves, in some sense, wide open to skeptics who are very quickly going to say, oh, that's a highly reflective seagull or something crazy like that. And that's just going to happen. And we're going to have to deal with that. And I would hope that the scientists out there who are going to be seeing this presentation will keep in mind that we are presenting initial preliminary results. This is not a definitive scientific analysis. This is not publishable. We are not at that point yet. We are working to get to that point. And we're still going to get the skeptics jumping and saying ridiculous things regardless. And as a close friend and colleague of mine, John Skilling, likes to say, a sufficiently motivated skeptic can deny anything. And we know this from flat earthers and whole hosts of other belief systems out there. So let me get started on our initial preliminary results. This slide probably isn't entirely necessary because we've talked about this a great deal already at this meeting. I really do like UAPx, or I really do like SCU's definition of UAP as unidentified aerospace phenomena. Because I think those are the objects that we're interested in most. So that makes a lot of sense. Here we're going to focus on unidentified aerial phenomena because we don't know what some of these objects are. Some of the things we've seen did appear to be aerial phenomena and possibly atmospheric phenomena. So we're going to have to keep that open for now. And of course, everything we talk about today and see, we are not necessarily assuming that they're all alien spacecraft. That would be ridiculous. And we all know that would be ridiculous. So, and we know that the vast majority of UAP or UFO observations are misidentifications. And they fall into many, many categories. And there are many possible prosaic explanations out there that need to be ruled out. And that's one of the important things to keep in mind about science, is that we work through the process of eliminative induction, where we eliminate possibilities. We rule out different scenarios or different hypotheses for a given problem. And you've probably encountered this when you go to the doctors and you've hurt your wrist, and the doctor writes out a script that says RO, fractured wrist, and sends you off to get an x-ray, and that RO stands for rule out fractured wrist, and that's fractured wrist, and that's what you're trying to do when you get an x-ray. So a lot of our work is going to be focused on ruling out prosaic hypotheses, all the prosaic hypotheses we can think of, and there are a large host of them. And you can imagine from imaging for 5 days off the coast of Southern California, there are lots of bugs. There are lots of birds. There are lots of paragliders. There's lots of helicopters. There's lots of airplanes. There are many, many things up in the sky, and this makes our job even more difficult. Now, I sometimes wonder why the extraterrestrial hypothesis is thought to be extreme or way out there, because that really operates under the assumption that Earth is unique. And we don't really know that yet. We don't know anything about the planets, in nearby solar systems. We knew very, very little about these places. And we do know now that many of these planets are in habitable zones. About 1 out of 5 stars that you see in the sky. So when you go out in the sky tonight and are looking for UAPs, take a moment and look at the stars. Count out 5 stars. One of those stars will have a planet that has this in the same temperature range as Earth, and very possibly will have a planet there. So that's 1 out of 5. And after you've counted out those 5, look at the rest of them. And we have to be cognizant of the fact that this is not that extraordinary of a hypothesis. I don't think that that's unusual. But we do need evidence for it. That's important. And we don't have evidence for the extraterrestrial hypothesis yet. We don't have So I've worked before with Robert Powell and Peter Reale here at SCU, and together we wrote a paper after the first SCU meeting where we estimated the flight characteristics of unidentified aerial vehicles, or unidentified aerospace phenomena might have been a better phrase now that time has passed. And you really can show quite conclusively that these observed phenomena or objects are traveling at really extreme speeds and extreme accelerations. And a lot of people have contacted me since we've published this paper and said, wow, this really blew my mind. This surprised me. I didn't know this. And that kind of surprised me, because this has been known for a long time. This has been known for 70 years. pilots have been reporting unbelievable speeds, incredible speeds, put quotes around those words, for decades. And no one's listened. And pilots have complained about these being air safety hazards. Nobody's listened. And at some point, we need to stop and think, look back and think, why didn't anyone pay attention to any of this? There's something rather wrong here. And I've had other people accuse me, actually in one New York Times editorial, of this being a simple analysis. And I had somebody ask me about that in a podcast once. Well, so-and-so in the New York Times editorial said that this was a simple analysis. And my response to that was, yes, it was. It's a simple analysis. It uses fundamental kinematics. That's all we use. That's physics 101. Any undergraduate could have done the same calculations we did in this paper. I didn't claim, none of us claimed that this was an extraordinary paper or some extraordinary feat of, mathematical wizardry or whatever. It's a simple analysis. And what's really sad is a simple analysis that any physicist could have done and should have done before speaking publicly about the phenomena. And we've heard lots of physicists speak publicly about the phenomena and talk about it as if it were nonsense. This is a calculation they could have done. It's a calculation their undergraduates could have done. But it clearly is a calculation that they didn't do. And that's what's significant. And in fact, to highlight this, I found out that I saw a newspaper article from a high school in Georgia where the physics teacher was using this paper as an example for the students to work from, where they could apply the kinematics they learned in their high school class to a real-world problem. And I thought that was amazing. But it highlights how simple the analysis is and how little work it really should take to get to the conclusion that these things are actually anomalous. And you then have people asking, well, why does everybody jump to the conclusion that these are alien spacecraft or that these are spacecraft? And the answer is simple. In one of these cases, it was the 2004 Nimitz case, the objects were observed, the tic-tac shaped objects were observed on radar moving at speeds that had to be at least, you can estimate what the maximum speed would have been 45,000 miles an hour. That's like Mach 60, and that's what we estimated. And this has been known for a long time. Hermann Oberth, who was the mentor of Wernher von Braun, who we have a poster of over there around the corner, he was his mentor, gave a talk on UFOs in 1954. You do the math, that's almost 70 years ago. 68, I guess. He gave a talk in 1954 and talked about how UFOs have been tracked on radar going at Mach 55. So our estimate from the 2004 Nimitz case, Mach 60, was not that far from Hermann Oberth's estimate of Mach 55. This has been known by physicists and aerospace engineers for decades, by some physicists and aerospace engineers for decades. The others haven't been paying attention, and that's a problem. So when people ask me, why do some people jump to the conclusion that these are spacecraft? The answer is simple. And anybody who knows anything about spacecraft knows that 45,000 miles an hour is certainly fast enough to get away from the Earth. And in fact, 45,000 miles an hour is about as fast as the New Horizons probe that we sent to Pluto is currently going. And that probe is leaving the solar system. So why would you assume that these are spacecraft? It's simple, because they move as fast as spacecraft do. I hope I don't have to say that slower for the people who haven't been following, but It's time for others to start playing catch up, unfortunately. Now, what are these things? And we all have that question. And it's difficult because we don't know that this is all one phenomenon. There are possible prosaic explanations. There are, of course, the possibility of hoaxes or misidentifications. These could be, we have the extraterrestrial hypothesis that I just mentioned. There are other hypotheses that are even possibly, I don't know if they're crazier or further or more extreme, but interdimensional, extra-dimensional, time travelers. There's a lot of possibilities out there, and there could be multiple things going on. And so that's one reason why this is going to be difficult to disentangle. I had somebody ask me recently, so how do you think UFOs move? How do you think they propel themselves? And I don't have a good answer to that because I don't think that these are one thing. And in fact, if somebody were to ask me, how does a car propel itself? I don't have a single answer for that either. There are gasoline-powered cars, there are diesel cars. Those engines work differently. There are electric cars, there are hybrid cars. There's many different varieties. And we probably have that situation too with UAPs. And I found I've given that some thought, especially since we have accounts of UAPs lifting off from the ground slowly to about 20 or 30 feet, hovering for a second, and then shooting off at an extreme speed. In the Lonnie Zamora case, I think that UAP had lifted off using some kind of flames, like a rocket engine, and then hovered and took off. So even a single craft may be using multiple propulsion phenomena. So who are we? Well, we were founded, UAPx was founded by Navy veterans Kevin Day and Gary Voorhees. Gary Voorhees is here, right over there, and he is now the president of UAPx. And we have Matthew and I and Christopher Altman are the recruited scientists on the team. And we are already a nonprofit organization in the state of Oregon and working to get federal nonprofit status currently. So, and our goal is to collect data, hard scientific data on UAPs, and to analyze this to the best of our ability and to make this data publicly available. And I'm going to hand this over to Matthew.
All right, so you just saw a diagram, so we'll show that again, that shows you how extensive the possibilities are for UAP. So I wanted to give proper credit for it, but realized late that it was clearly a pseudonym. So those of you who are fans of Star Trek Next Generation might remember a character, Berlinghoff Rasmussen. So love to give proper credit for whatever ufologist came up with that image, did an amazing job, but clearly wants to stay anonymous. So I hope he or she is okay we use the diagram. But that diagram reminded me of something. So in my own day job field of direct dark matter detection, we have this problem, which I put in quotes, not necessarily a problem, it's too many concepts, too many ideas. So we have all these different possibilities for what UAP can be, and that diagram reminded me of we have all these different possibilities of what dark matter could be. Now, when I show this slide to scientists, they say, but yeah, but that's serious science. But we're arguing UAPs are also serious science. So that we know that the times are changing now in academia and education. We just had a talk yesterday. I'll mispronounce his name, unfortunately. I can't try to say it, but we had an esteemed professor from the University of Würzburg in Germany, who may be one of the first, if not the first, in the world to formally and officially allow UAP studies to be conducted. So their physics department is actually treating this as connected with SETI. So I encourage you, you saw us talk yesterday. Here are links to their department, their website. So in the media, we know that UAP are covered by an increasingly number of news outlets, and that we've got New York Times, 60 Minutes, and that the mainstream media have not been playing the X-Files style background music as often anymore. So there is still, though, this circularity. Maybe the circularity is finally broken. The circularity, though, in this field is that it's nonsense because there's no data. Why is there no data? Because it's nonsense, so you're not allowed to collect the data. So it's a circular logic, and it's very hard to break through that logic because it takes time, effort, people, and funding. So UAPx had a goal. So Gary Voorhees and Kevin Day devised a plan to revisit an area off the coast of California to get data, just like I was saying we don't have. Except that we do, but we want to get even more data and get our own data where we had known the data provenance. So Gary and Kevin came up with the idea to do this with a team of civilian scientists and revisit the area near Catalina Island. Why? Not only was it is a potential hotbed of tic-tac activity, which is not necessarily an isolated or rare circumstance, but it is the proximate location of the famous incident with the USS Nimitz and the USS Prince on the West Coast. There's also the East Coast, and there are other instances. But also this area seems to have, if you talk to the locals even, that they're going back decades, that this is a potential hotspot. We don't know that statistically, but this seemed like a reasonable idea. And what's some of the inspiration behind this? How likely is it that the pilot's eyes deceived them at the same time, that the FLIR and the radar all had a glitch due to a software upgrade? Glitch due to a software upgrade for the best, most funded military in the world, right? Has glitches all the time, right? No, that doesn't really make any sense. How about the upgrades of our systems, instead of creating software bugs, might actually explain why new objects become visible? Because we got new, better technology. So here, in this case, why was the 2004 encounter so compelling? You have high-tech U.S. military equipment combined with trained observers. These aren't the kinds of observers that psychologists make fun of when they show that eyewitness testimony doesn't work. This isn't Joe Schmo, Joe Q public observer on the street. These are military pilots, okay? And why are we not listening to the testimony of our own pilots? So the idea here was to collect our own, though, actionable data so the men in black or the men in khakis don't come take. And then, of course, we made a bajillion copies of this data. We wanted to collect our own actionable data, try to start figuring out what these things are. Is it ET? Is it foreign actors? Human? Is it mundane, prosaic? And overcome the problem of one blurry image in just one camera. So our goal was multiple cameras at different wavelengths of operation. We didn't always succeed in that goal. Some of the things we have were only caught by one camera, but remember, this was just our first attempt. We also brought non-electromagnetic equipment, as detailed later in this talk, because it's not just as simple as we'll look at different wavelengths of the electromagnetic spectrum. You have to think out of a bigger box than that. And we had multiple teams. So we had, so Kevin and I were at a house in Laguna Beach where we deployed a lot of equipment on the roof. Then we had a team on Catalina Island, and then we had Jeremy McGowan in the Osiris. Details on that later in the talk. So he was mobile in his car. So what was our equipment? So we had 8 forward-looking infrared cameras. That's long-wave infrared, so similar to those used on U.S. fighter jets. These are from Washington State engineer David Mason. And then we have the UFODAP visible light camera developed by Ronald Ulch. And so it's visible light, but it's partially infrared for night. So there's the link to UFODAP website, Ron Ulch, highly recommend. And then we also had something that almost nobody ever has. So we also had radiation detection. So we had what's called the Cosmic Watch from MIT. Everyone was asking me, is that the Geiger count, like a Geiger counter? I say, this isn't 1950 anymore. Okay, Geiger counters, we have much better technology. Geiger counters that's for when you need radiation detection on a television show. Okay, this is 2022. This is far superior. It tells you not just the energy, but the rate. So, it tells you the energy, not just rate. So not just click, 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 click. which tells you just how many counts you have, but what are the individual energies. Why? Why did we think of this? Because you've got, for example, the several hundred-page French report. I'm not talking about the Cometa report. There's a more recent one that mentions cases of radiation. So I had, before there was an official translation, I had my wife finding the juiciest bits and translating the juiciest bits of that. And I'm like, why is this 300 pages? Why is the United States version of this report 9 pages of nonsense and obfuscation? And there were juicy bullet points about cases of radiation sickness. So I'm like, great, because that's data, that's key information that says we don't just rely on camera, we also look for anomalous levels of radiation above normal background. That's also very hard to fake. Okay, so now we also had so much more. We had from David Mason, night vision goggles that convert light into sound, regular but very good binoculars, night vision binoculars, and also a second radiation detector from David that we could use to cross-calibrate the cosmic watch. We also had a quantum random number generator that Chris will be talking about, and an oscilloscope to plug into the various equipment to debug and study the various different results. So here is a picture of our setup. And you can see a display of all different FLIR cameras and the oscilloscopes, but it's extremely important to keep in mind, even with the setup, that science, though, is not in the equipment itself, it's in the analysis. So you can show up with 50,000 pieces of equipment, but if you don't have the people who have the intellect to do the analysis afterwards, this by itself is not good enough. So people have been impressed by equipment, but the thing is we also need to analyze the data that we got. It's not enough to just have the right equipment. So what was our initial strategy for beginning the analysis of our data? So first, image processing is a very difficult problem. We know that within computer science, just think of CAPTCHAs for catching robots. We have a link to a YouTube video as a joke. You know, there's a Geico commercial with a robot that's getting very angry. Is that a 5 or an S? So how many of us have had that with CAPTCHAs? So UAPx has its own machine learning algorithm built into it, but the FLIR did not. It was not the most contemporary FLIR system. And in fact, we had to deal, of course, with cursors, temperature scales bouncing around. So using relevant experience that we could bring, that I brought from a graduate school of working on bubble chambers in old school physics technology, but one that requires image processing, is that I started developing within the team a image processing software specifically for infrared that doesn't exist, but is inspired by all the existing image processing algorithms and techniques out there. But again, we didn't start there because the image processing is still a very, very difficult problem. So the approach we took was to look at the radiation first, since that's just text files of hits and energies. So it was a two-pronged approach. Look for high energies as well as high rates above normal background radiation. We also made sure we had thousands of hours of calibration before and after the expedition by us and others, so that we don't mistake something as an anomaly that isn't anomalous, but just happens to be rare. So not all anomalies are interesting, even in the radiation detection. So that you can get all kinds of peaks in high rate or in high energy or both in the cosmic watch from things like solar radiation, galactic, distant black holes, supernova explosions. There are particles that have been traveling for billions of light years that happen to interact in the upper atmosphere that day, create secondary particles that then hit the cosmic watch. And it looks like it's anomalous in high energy, but it's just your everyday, astrophysical events. And so this is extremely important to keep in mind. So the range of something like the cosmic watch is infinite because it depends on the flux of the source. So what is interesting is not just an event where you see high energy or high rate of radiation above background. That by itself is still not interesting. It is interesting if it's in coincidence with an anomaly in one of our other sensors or an ambiguity in one of our other sensors, like the visible light camera, like the UAPx or the FLIR. So it's the combination of the multiple modalities of different sensors showing something strange at the same time that makes for a more compelling case, that makes it less likely to have a prosaic explanation. And again, we have calibrations not only of the, I mentioned, we've driven, I've personally driven the Cosmic Watch across the country to get data at different latitudes, different altitudes also. Make sure that, oh, well, it's just natural for the area that we're in to have slightly higher natural background radiation. We also have, so for the FLIR, we had, years, Dave Mason spent years working and looking at that. So we have a lot of calibration that's not in the movie, because that's a boring movie. Nobody wants us to hear science talk about how we spend all this time making sure that the equipment was functioning properly and that we had good background calibration. So we started tabulating. I said we started by looking at the Cosmic Watch data. So this looks like gobbledygook, not only to you, but also inside the team. I know we talk about how the system that I came up with is kind of opaque. I started tabulating what are the most interesting events in the Cosmic Watch. So started using Greek letters for the interesting energy in order from the highest down. And then when we ran out of Greek letters, followed by Hebrew, and then numbers used for the ambiguously high rates. So in the upper left, we have events that seem to be oddly high in energy. Column G notes use Roman letters to identify clusters of events and interests across both categories and time. And then you have yellow and orange highlighting as well for different clusters and types of events. So we took our results from the MIT Cosmic Watch, and we can convert the voltages in that device to an energy, to an approximate energy, or an approximate energy per unit distance traveled in the device. So normal is something like 2 MeV. So MeV, it's a unit called mega electron volt. So don't worry about that. It's just that 2 is normal. As average. Normal range is less than 8 for terrestrial radiation. We had things as high as 40-something, which is interesting already, except, like I said, some of these are just going to happen statistically. You are going to have events at high in energy because you have naturally occurring cosmic rays. For rate, our normal rate was about 0.3 to 0.5 hertz, and so hertz is number of counts per second. And as you see on the lower right, we had some instances as high as 1, 2, 3, so significantly higher than average. Some of these, though, so the ones that are not in bold, are events that we're able to seemingly rule out, at least initially, as being related to solar activity that week, because that week there was what's called a CME, or a coronal mass ejection that could increase radiation even at the surface of the Earth. But there are still events that are in bold that were not tied directly in time to instances of high solar activity. So going back, though, for a moment, so that was the Cosmic Watch. But going back now to the FLIR and to the UFO DAP, talking about image processing. So we wrote a neural network-like package called CTAP. So that's the acronym that our acronym genius Jeremy came up with, Custom Target Analysis Protocol, to be able to now couple to the radiation analysis. Obviously, we can't forget our objective, obviously, for a UAP analysis. Well, what about pulling out images from our imagery, from our videos? So motion detection programs exist, of course. They are everywhere these days, but not for infrared. And also, they're not all very good. They're either too sensitive or not sensitive enough, or both, or they're opaque. You just stick it in the machine learning algorithm, you get what you get. So we just wrote our own thing from scratch that has 2 phases. Phase 2 does not exist yet. Phase 1 is to classify anything that's an object. So something crosses the camera. Don't worry about what it is. Let's just see something crosses the camera. So that's phase 1. To discover what are actual objects that are crossing the camera. So what we have is, in phase 1, is figure out, okay, we have something that crosses the camera, but it's not a cloud or camera noise or something like that. After this, we do this for the FLIR, then we'll do this again also for the UFO DAP, which has its own algorithm to do this, but also to cross-check it. So the idea here is is, so on the right, this is the, we fit skew Gaussians to the probability density of what this is this is the standard deviation of the 3 RGB values in the camera. And what we found is that it's more likely that for noise, that it's going to go up uniformly in R, G, and B. So if it's a bolometric discharge or some other kind of camera glitch, it's going to be more probable, it turns out, that the RGB values will go up uniformly in intensity. Whereas for something like a bird or plane or UAP or something that crosses, it's not going to go up uniformly in the RGB values that's rendered. Now, this isn't the raw data. The FLIR just does the temperature. The RGB is another step of rendering. So in the future, something we want to do is go one level deeper below this, and Kevin's working on that to get the raw data of the FLIR, so we're not just looking at the software's rendering of RGB. So this still isn't good enough because this is a FLIR camera, which means the RGB is an artificial software layer. So, but nevertheless, we were able to use this to be able to help figure out what was a glitch or noise or not. As you see, there's still overlap, of course, so it's not perfect. So there's overlap between the red and the blue distributions at very low levels of standard deviation of the 3 RGB numbers. But you have this really long tail where the vast majority of the blue is events that we know are real. How do we know they're real? By combining human eye hand scan together with iterations of this software, early versions of it, double checking each other, not trusting a human or a computer, but rather together to try to test on a couple hours of sample data whether the software is working before you trust to deploy it on the other few hundred hours. So what does the result look like? It's not a neural network, but it's very similar to those who are familiar with it, is we get this beautiful peak in blue of things that are signal-like and red things that are background-like. So this is actually a combination, though, of different approaches. So this is not as simple as something that's above a certain threshold means it's a real event. That's not good enough, because then you trigger on things like noise, camera glitches, and clouds moving also. So we don't just have a minimum, we also have a maximum threshold combined with the probability density based on the standard deviation of the RGB values. So we combine different aspects of, some of this is like a naive Bayesian classifier, familiar with that terminology, and some of this is more neural network-like, but it's really a combined approach of aspects of both the top-down and the bottom-up approaches to AI ML in order to tackle this problem. So now, this is, so the video that we use as to test this, so we used 1 hour on July 14th that was just chosen by Gary at random to give me. And so the code caught, the software CTAP caught 70 out of about 80-some events. The remaining missing ones look like pretty obvious insects, dragonflies, things like that. But that 80-some, that was after hours of looking at over and over again. If we actually looked at the video the original way we wanted to, which is just sit down and stare at the video for an hour, we estimate that the software is 2 times better than human efficiency. So you would have missed significant numbers of these events. Later, you're going to see events that will show you they were only there for a couple frames. You're not going to see that. We found anomalies, we found strange events. They're just there for a few frames, and you're not going to catch that, but the software caught it. There is still a false positive rate estimated to be 15 or 20%, because you're not going to get rid of the fact that some nights, some days were cloudy, and you still have some camera noise. So this is definitely not perfect. But the way CTAP works is it converts the MOV or MP4 files into lossless full-resolution BMPs. So we can't do that for the entire, that would be hundreds of terabytes if we actually expanded each of the 3.5 gigabyte videos of 1 hour. So what the system was that we had computers that would take 1 hour video at a time, expand it out into frame by frame, which then takes up 600-700 gigabytes on your hard drive, then finds the objects, deletes the frames that don't have objects, and then reassembles the movie into a shorter movie that just has the objects of interest. So instead of wasting terabytes and terabytes, you only have tens of gigabytes now. Again, it's not perfect. It missed some events. So of course, we'll go back and make sure at some point and make sure they didn't throw out anything important. But that's why, again, we tested it first. And that's also why we're partnering with SCU, so that SCU members are going to help us with phase 2 now, which is to classify things we found. But instead of going through 600 hours, it's only going to be 1 hour of just from the entire week pulling out anything that crosses the screen, instead of wasting time staring at the screen of blank video. And I'll tell you, that doesn't work. Not only do you miss things, you start to imagine things that aren't there, because the human brain gets bored. You cannot stare at a computer screen and look at an hour of FLIR video or UFO video. It's not going to work. You'll imagine things that aren't there because your brain gets bored, and you're going to miss important things that are 5 pixels in the corner and you didn't see it. So this has been working very well. And the images, though, the frames that are being used, I didn't mention, it's not just looking for an object in that frame, but it's a trick that I used back from my PhD grad student days. It subtracts the previous frame, so it looks for differences. So it's not, because that's much easier to find something then. It's not just looking for an object in that frame. It's looking what's new in that frame that wasn't there in the previous frame. And that's very powerful, because then it's also agnostic. And you're not just looking for hot objects or anomalous cold objects. You're looking for both. And so because you're doing pixel subtraction, what's happening is that you have temperature going both up and down. As the object moves across, it leaves a void that is then flagged by the pixel subtraction algorithm. So what are the most interesting events we captured that we're going to be telling you about today? This is not a chronological list. This is a list in order of what we think was most important and most interesting. The number one most interesting item of interest is a potentially radioactive atmospheric ambiguity. We're very cautious in our language. Like Kevin said, it could still end up being a nothing burger. We have to test all the mundane possible explanations. Our second most interesting event that we'll be regaling you with this morning is a slow-moving, monotonically glowing sphere that was potentially captured from multiple angles using multiple sensor modalities. So we have another interesting, but we don't have time for it today, but we mention it. It's not in bold. In bold are what we decide to cover today. We also had what appeared to be objects raining from the sky into the ocean. They do not look like known FLIR camera glitches. It doesn't look like rastering. It doesn't look like dead pixels. It does not look like a bolometer discharge, because we have examples of all those things from calibrations and from study hours. It doesn't look like one of those things. We have countless other examples. So we could go on for 8 to 10 hours, but we have 2. So we're only focusing on the 2, what we flagged as our potentially most interesting ambiguities. We had transient lights in the sky and the island and the ocean. So we don't have time to talk about those. So we're going to talk about first our strange hole or tear in the sky. We don't know what it is. And then our Wednesday night drama in the middle of the expedition that takes up a significant portion of the film. So what is our number one most interesting event? So on the morning of July 16th, around 4 a.m. local Pacific time. So we didn't know this until months later. It's the way I just stated it sounds like this was observed live. It wasn't. This was in the post analysis. We saw this. So we have a high energy event that was labeled on an earlier slide's gigantic table that I had. This was labeled as the highest energy event we recorded, about 40 mega electron volts. We don't know what type of particle this was. We don't know the direction. We need money for that. Better radiation detectors next time. We don't have that. So everyone always asks, do we know the direction it came from? No. Do we know the type of particle it was? No. Do we wish we had that? Yes. That takes money, that takes investment to have better detectors, better equipment than what we had. But we had what we had. And most UAP studies don't even have this. They'll have, at best, a Geiger counter that doesn't have USB, because it's a Geiger counter from 1950s, 60s. So this, at least, we can at least get the data. So by itself, this is not necessarily remarkable, because as I stressed earlier, naturally occurring cosmic rays go orders of magnitude higher than energy in this by billions and trillions. But nevertheless, in the local time frame, you see on the left that this was, for the local time frame, this was a pretty high energy event that was recorded at 4:01 a.m. local time on July 16th. So it's definitely worth checking whether the other instruments saw something. So our estimates, we're still finalizing things like the systematic error on this. How unusual was this? So our current best estimate is that we should have seen at how many events of this energy during 1 week of data taking at that location, at that altitude and latitude. It's a 2 plus or minus 2. So for those of you who understand statistics, that means 0 or 1 would have been extremely normal. So by itself, this is not yet unusual. But what this means is let's check the other sensors to see, was there something strange at the moment that that high energy particle hits. And it's only one particle. This is not an increase in the rate of radiation. This was a one-off thing. There is something slightly higher in energy earlier, though, so if you look at the full timeline, this does seem to start looking like an interesting event cluster. So at 3:57 a.m., you have a 23 MeV particle, and the UFO DAP appears to trigger triggers on what appears to be a hole in the clouds that Kevin will be showing you next in a couple slides. 3:59 a.m., the UFO DAP system finds odd dots in that hole. And at 4:01 a.m. is where we have our 43 MeV per centimeter event. So I should stress that 43 MeV is not the energy of the particle, it's the energy detected. So you could have something much higher in energy and you're only catching what goes through the 1 centimeter of the device. So now we are starting with these correlations with other events happening so close by in time is where it starts to get interesting. So now I'm going to pass it back over to my colleague Kevin, who's going to tell you what we found in the UFO DAP.
Right, thank you, Matthew. So I'm very glad you were here to explain your fine work on CTAP, and that'll really help us go through the 900 hours of FLIR video. And as Matthew explained, we first used this cosmic watch data looking for anomalous particle detections to see if we picked up anything on our other sensors. So when this was found, Jeremy McGowan went back to the UFO DAP and looked to see what was being imaged at the time of the 43 megaelectron volt per centimeter detection. And he found something which was rather interesting. So I'm going to first show what he found, and then I'm going to show a video from slightly before that. So let me escape from here. So this is the video that correlates with the time of these particle detections. So first we had the 23 megaelectron volt, is that correct, particle detection, followed by the 43 megaelectron volt. Oops. So the UFO DAP triggered on this, and very quickly, took a very quick picture. And if I can get it to hold, I took the frames from the other videos, but not this one. Evil. It's hard to do this without my mouse. I can't move the track pad fast enough there. There we go. All right. Let's go back to this. I think we have a first still of this anyway. Yeah, that's a problem. Clearly. There we go. Here's the still frame from the video. And what you can see here is this is looking out toward Catalina Island. The island's off this way. It's foggy. You can see the lights here. These lights are from the city of Avalon in the harbor. There are lights down here underneath this text that's written on top of the image. We have images without text as well. These lights are from boats in the channel. This here is a reflection on the camera. And we have this ambiguous black spot up in the clouds. So this is what the UFO DAP triggered on at this point in time. And it's not clear exactly what this black spot is. And so this is one of the things we're looking at. I wouldn't necessarily call this anomalous at this point. It's ambiguous. We don't know exactly what's going on. And the first job is to try to rule out other possibilities. So I'll show you what another trigger looks like. This is from slightly before, same day. This is from 7 minutes before. Oh, when I do that, and there it is. The UFO DAP triggers on this bug. I'm going to start it over, and you'll see this bug zipping around in front. It's not a fast walker, sorry. It's a bug. And triggers and then kind of loops around. The bug actually comes into the scene again, and it keeps triggering and moving. So this is how the UFO DAP system works. And you can see there's no dark spot in the sky if we were to go back through that carefully. So 7 minutes later, you've got this ambiguous dark spot in the sky. So it's just a dark spot in the sky. Is it on the camera? It's not clear. I'm going to go then to the next video, which was taken not much longer after. This one I'm going to go frame by frame. I think I'll play it first and then go frame by frame. So I pulled all the frames last night. Those of you who was wondering what I was doing while we were eating pizza, that's what I did. So there's the hole in the sky with the bug, and it triggers and moves. So what's a little disturbing is how the hole behaves when the camera moves. At first, the hole doesn't seem to move with the camera. And I'll show you what this looks like frame by frame. So here comes the bug on the left. You can see the dark spot in the sky here or on the camera. And as the camera starts to move, let me back it up a little bit. The camera is going to start moving now. It starts to move, and first thing that happens is the hole doesn't move as much as the lights from the boats do. And in addition, we get these white spots here, which we do see later. We see something like that later. But we also see these dark spots, which seem to be some type of residual effect from maybe from white spots there. So it's not clear what's going on. But it's suggestive that this is some kind of artifact. And the hole is still rather much in place and then kind of disappears as the camera pans. And then things again settle down. You do see other dots appearing every now and again. There's one here and here, and these are probably artifact. But all of these camera behaviors have to be studied very carefully to figure out exactly what's going on. And that's going to take a lot of time. So I know we are focused on transparency, but we ask that people be patient. Science is very long and boring and tedious. There's a great quote from The Simpsons from Principal Skinner on how science has everything, is sitting still, being quiet, and I forget exactly how the quote goes, but science has it all. So this is going to take time. All right, so the primary event, though, happens about 3:59. So we do have images of this hole with nothing in it. And then at 3:59 a.m., this is what the video looks like. It's very quick. It's only a few frames, 16 frames or so. I'll show you each of the frames. So here's the video at 3:59. So this is 2 minutes later. So you get a dark spot in the sky, apparently. 2 minutes later, that spot is still there. And now we have those white spots sitting there. And those whites and spots like that appeared in the previous video when the camera was panning. So we're suspicious that they might be artifact. And I'm going to advance the frames here. Frame 5, 6, 7. And you can see the hole starts changing. So I'm backed up to 4. When I say 7, you'll see it start to change. So 4, 5, 6, 7, 8, 9, 10, and the hole's fading. 11, 12, and 13, you're going to see another dot appear right around here. So watch this area where the arrow is now. 13, there's that dot. See it? I'm going to go back and forth, a tiny little dot. I don't know if you can see it on the video monitors. Hopefully those of you at home can see it. Another dot appears, and it persists for the next 3 frames. Yeah, 3 frames isn't a lot. We know that. There was a lot of disappointment that we were not recording much longer. And that's another lesson learned. So this is ambiguous. We don't know what's going on. We're not sure whether it's an artifact, whether it's some kind of anomaly in the atmosphere. It's possible it's a hole in the clouds. It's possible those things are objects. Some people have looked at this and made some glib remark, oh, they're probably seagulls. Well, yeah, that's easy to say. We can do some math. All these dots are located where the hole is. You don't see that anywhere else in the video, all right? So what's the area? How many pixels does this hole cover? Well, it covers roughly 114 by 128 pixels. And the whole screen is 1920 by 1080 pixels. So now the relative areas come to 0.007, James Bond, right? So it's 0.7% chance that one dot is going to appear in that hole. I count 53. Let's say I was a little excited in my counting because it's hard to count. I'll show you a picture later, blown up. Let's just say it's 40. So the probability that all 40 dots, that 40 of those dots are just going to appear in that spot on the sky or on the screen or in the image is 0.007 to the 40th power. You can pull out your calculators. I know you all have them. And if you do that, the answer is about 2 times 10 to the negative 87th power. So it is 0.00086 of those, and then a 2. What's the chance that 40 seagulls are going to be in the same patch of sky? It's 2 times 10 to the minus 86th power. Scientists need to be more careful before they make silly comments. Do the simple math that your undergraduate can do. Thank you. So we don't know what this is, and that's what the investigation is about. That's what we're here for. I'll show you a post-event control. So that was at 3:59 a.m., 4 a.m., 1 minute later, it triggers on a bug or something again. There's a bug, and it zips off. But you can see, if I'm going to click here, you can see there's no spot in the sky. That spot is gone. The white dots are gone. So that's 2 minutes later. Whatever that ambiguous thing was, whether it was on the camera lens, an artifact on the CCD, a hole in the sky, a hole in the clouds, whatever, it's gone 2 minutes later. So this is strange. And yes, strange things happen. It's important to acknowledge that. So now this is basically what one of the events we're studying. Let's look and see what the assumption that it's a hole in the clouds means. Can we rule this out? There are holes. Holes do appear in clouds. They're often called fall streak clouds. Planes can cause them to happen, a plane flying through a cloud. In many cases, this happens when you have supercooled water in very high altitude clouds, and something moves through the clouds and causes a crystallization to occur. So you get supercooled vapor, then crystallizes, the crystals fall out, and you get what's called a fall streak cloud. This could not have been that kind of fall streak cloud because the cloud ceiling was only 1,700 feet, and it was, I don't have the temperature here. Do you remember the temperature? It was like 90 degrees or something like that.
According to UFO, that was 91.
Yeah, 91 degrees. Oh, yeah, it's written on the screen. Yeah, so it was about 91 degrees. So you don't have water vapor crystallizing at 91 degrees, even at 1,700 feet. You can still get fall streak clouds happening where you get vapor forming droplets when you get planes flying through. So something above the clouds or moving through the clouds could have caused a hole. That's possible. Let's see, the speckles that we see, those spots, our first thought was that the spots were due to the radiation we were detecting. And we thought that this might have been due to the coronal mass ejection that happened that week on the sun. So there was a large explosion on the sun. The sun spit out a burst of particles off the corona, and that headed toward Earth. And we did detect these with the Cosmic Watch. But they are also not going to fall into the same patch of the CCD. They would follow the same probability rule as the seagulls. It would be a 2 times 10 to the minus 86 chance of them all falling into the same place. So that's not going to happen. If it's radiation, they should be equally distributed across the CCD. Cameras do not focus gamma rays. So they're not stars. First, they're too dense. We're in the LA. We're 10 miles from Los Angeles. You can see the city lights easily reflected in the clouds. Even when the stars were out, you couldn't see them that clearly. So they're not stars. So we don't know what those things were. We don't know if they were objects or if they're artifact. We have looked at Doppler weather radar data, and we are currently working to study this in more detail because we don't know the area well enough, nor are we weather radar experts, to know whether this is normal or not. I can show you what we found that day, but I can't tell you what's typical, which is critical. So this is Catalina Island. We are off in Laguna Beach, which is around here. And we did see that there was there were basically some turbulence in the atmosphere. This is the wind velocity at altitude. And you can see you're getting some high winds up in the clouds, close to where the cloud hole was, not exactly where the hole was. And this here is radar reflectivity. So we're getting some radar reflectivity in the similar area. And that suggests maybe there was something up in the clouds or above the clouds. But again, we have to check to see what normal is first. We have to do a background study. So this is suggestive and interesting, but all it does is keep us going. So solar activity, we can have solar activity, and we did have solar activity during that time. You can also have cosmic rays. Cosmic rays are constantly raining down on the Earth. And CCD cameras will react to other forms of radiation. And in fact, there are dark matter experiments based on this that rely on CCD cameras. So we did see some solar activity. I will show you a video of this. And it was exciting when we first saw it because we did not know what it was. So this is an example of what solar activity looks like. That's the same scene. And it's going to start out looking at Avalon. So here's, I think it's already started moving. This is Avalon here. These are some boats out in the water, very similar to the previous imagery. The hole in the clouds would have been here in the previous pictures. The camera's already panning over. And it is long enough that I can actually control it with my mouse now. So we're panning the camera over. And now we see some of these spots that appear when we're panning that look like the spots that appeared when we panned past the hole. So this is relevant for study. And we see a lot more of that now as it's panning and getting toward the light. It's passing over the city lights. And then now you're looking up and seeing part of the antenna on the UFO DAP, but you can see there's lots of little speckles pretty much uniformly distributed across the screen. Not so much down here right now, but that happens. I'm going to play from here, and if you watch those speckles, you'll see they just kind of sparkle. And we were very excited by that and wondered what we were seeing. I'll play the whole thing again. And we then looked at slideshow. There we go. Yeah, so we looked into the solar activity, and we were able to tie this to a coronal mass ejection. And so we think that those sparkles that you saw in that imagery was actually due to particles from the sun that were raining down on the Earth at the time. And that potentially is a discovery in itself. So the sun was very active that week during the trip. That's inconvenient, but it's something you can't control. This is data from SOHO, one of the solar observing observatories, one of the telescopes. And this shows the different rates of solar activity. The sensors aren't working all of the time, so we do have missing areas. So it doesn't explain that strange hole in the clouds that we saw, nor most of the events that we saw, but it does correspond to some of the radiation events that we saw in the cosmic watch. It appeared to be related to increases of rates of particle detection, but not the energies. So here again is that mysterious hole in the clouds that you all got to see in the movie. And is it a fall streak hole? That's still a possibility. And let's see here. There we go. So here, as promised, this is a zoom in of those spots. Are they thermal noise in the camera? That's a good question. We looked at the statistics, and they're non-Poissonian. So we don't think it's thermal noise in the camera, but it could be some kind of other noise. We don't know what the dark spot is, and we don't know why it disappeared or how it closed so quickly, if it was a hole. So there's still some ambiguity here. This is a map I made, a correlation map, where I took those 16 frames, and I took points well within the hole, and I just mapped out the the change of the intensity of these pixels over time. And then I used that function and I did a cross correlation between the behavior of these pixels and all the other pixels on the image. Should basically, so this basically is a picture that shows you what pixels on the screen are behaving like the pixels in the center of the hole. So of course this defines the hole quite well and allows you to get a good picture of its extent. So everything that's been painted blue is highly correlated with the closing up of that hole or the disappearance of the black spot. But you see that this is not limited to where the hole is. You do have correlations in other parts of the sky. And if you look at this carefully and go through this numerically, you see they are limited to the clouds. So it suggests that it's a cloud behavior and not an artifact with the camera or something on the camera lens. If it was something to do with the camera lens, then I would expect that the lights down here in Avalon, or even more probably the boat lights down here, would have some kind of correlation with the behavior of the light in the hole, especially since we're getting points way over here that are correlated. So this suggests that it's not a camera artifact, it's not something on the lens, it probably is with something to do with the clouds. But this is going to take a lot more work and a lot more investigation, and we'll see if we have something publishable when it's done. And next up, we have Christopher Altman. Do we have him in comms? I'm going to stay and advance the slides for you.
Yeah, okay, that would be great. I'm going to prioritize audio because I'm not sure about my bandwidth. I don't want the call to drop. So for the slide, I can't see the slide now. All right, so we wanted to find corroborative data, and so we contacted a lot of different places, including the Doppler weather radar. The radar showed that there were metallic objects in the same area, and so we also sought out gravitational wave data through LIGO. Unfortunately, they were offline that week, and there was another one in Italy that was under maintenance. And we contacted California to see about earthquake data. There was nothing there. Dr. Sarah Little from SU has helped Kevin to start getting data with infrasound sensors that are deployed right around the area in the Pacific. And we saw a cosmic ray neutron, but it was not at the exact same time. Now, a lot of our time was not exactly correlated to the millisecond, because a lot of the times there were cameramen moving around our stuff or unplugging it, and so it was not ideal. So we were a few seconds off, a few seconds plus or minus, as opposed to the ideal of being, a millisecond time precision. So that's it. That's all. We look for gravitational, seismic, infrasound, neutron detectors with the Cosmic Watch, and we found some interesting correlations. And we're still looking for more. Next slide. So yeah, we through Jeremy McGowan, we did a Freedom of Information Act request, which is allows you to get information from the government so long as it's not classified. You can make the request, and usually, if there's not a backlog, they'll be able to get your answer. And so we sought out anything that was unclassified in the area. There's a lot of Navy ships in the area, so things like Navy deck logs, any satellite imagery, any radar or sonar data, anything that they would have that would be online and potentially accessible through the FOIA. Now, they were most of the stuff that we've requested was deemed FOIA exempt. We actually got a record fast response that only took days, and they said it was FOIA exempt, but it was kind of anomalous in and of itself. Next slide. Because the reason it's anomalous in and of itself is because we also did a FOIA request for the same area, same long, and say 15 minutes later, 15 minutes prior, and that data was not exempt, so it was accessible. So they said it's available, and so it's only the that long and time of the anomaly that was the data was exempt, and there was no reason given. Now, if you look at the commercial data, you have several satellite companies. Maxar Enterprises is very active in the news right now because it provides Ukraine data for the ground high resolution ground imagery for Ukraine right now, and it's also missing only for that time period. So it's not something that you would expect at all. So we're continuing to put in more FOIA requests to different agencies and different potential sources of information from the area. But Kevin also had this idea with to do satellites prior to this. So it's not the first time that we've requested these kind of things. Next slide. So yeah, the question is if it's our own military, it could be black ops, potentially it could be the reason it's exempt is because it could be a experimental aircraft or experimental drone of sorts, and they would not allow that to come out if it was a top secret program. So Jeremy put in the request for that, but he's got a lot of information, experience with these because he writes up proposals, and he's a technical expert for drone programs, especially the cutting edge prototype drones that are would be classified if this was actually what it was. So what we would think that it would be an unknown human craft as opposed to an unknown alien craft for Occam's razor, except for the fact that we would not be flying these things around to mess with our own pilots on our own backyard, because it's a potential accident, it's a potential hazard. So you don't want to have an accident happen. It's definitely not going to be the Russians or the Chinese, because they would use it on us. And so the question is, where is it? What is it? And Congress is actually looking into this now, and they've definitively stated that it is not U.S. black programs or anything like that. Next slide.
So, Chris, this one's back to me.
Great.
All right, thank you, Chris. So now I'm going to take back over here, and we're going to talk about the efforts that Kevin and I, in our home state of New York, have done to contact the Office of Senator Kristen Gillibrand. Not just asking for moral support and funds, of course, but also FOIA help now, too, since she's our senator. Our senator is also Chuck Schumer, but I think he's even a little bit busier, right, as the majority leader. She's known for having written the UAP Transparency Amendment to Defense Spending Bill with co-author Marco Rubio. Now, how many things do you know that are bipartisan? Right, UFO is one of those things. Points we've been trying to raise with her staff, unfortunately, they disappeared months ago, haven't heard back. This is no longer just a national security or global security issue. If they're unknown craft, if they are craft violating our airspace with impunity, or even aviation safety. But also there's the human health and safety factor. We talked about radiation. Don't forget the Cash Landrum case, which is one of our inspirations for bringing radiation detector. So it's a health and safety issue. The public has the right to know what the hell is going on here. It's different levels of safety here. So so we talked about our number one most exciting event. What's our second most exciting? So now I'll be happy to talk to you, very happy to talk to you about our second most interesting event. It's not even it's not a distant second. It's a close second, a different type of interest. This event was Wednesday, July 14th, 2100 hours, 9 p.m., so about 9:20, 9:30. We got a phone call from the island team. So from the Catalina to Laguna Beach is how it all started. So UAPx team members Michael Hall and Dave Altman started tracking a fuzzy, glowing spheroid. It was not blinking like an airplane. Appeared to change direction. It's not satellite or the ISS or meteor. With caveat there, shaky camera, right? So this was not a stationary camera like our FLIR. So we have not definitively. We have not definitively shown, but we do have their word that it was changing direction, because they could also see with their eye. So it appeared to change direction, slow down, accelerate. So this implies not a satellite or the ISS or meteor. We did see plenty of planes. It's not a plane. I'll give you guys an example. What does a plane look like? So one of the key things we're doing on UAPx, this is very important, is we show examples of mundane objects. So if someone out there says, oh, what you just saw is X, then we whip out a video. No, this is what X looks like. You're wrong. That's not that. So we have countless examples, as Kevin already said. Parasailers and helicopters, airplanes. This is what an airplane looks like in the night vision. I'll show you. So just bear with me a moment, because we have so many gigabytes of videos that we couldn't embed them all in our main talk slides, because then you would double click the talk slides and it would crash your computer. So that's why we have all the videos separate. So sorry for that, but we have just give me a moment to pull that out. So under mundane, and I have a whole folder called mundane and prosaic. So here you go. Here's a great example of what an airplane looks like. So you're going to see a dot appear, and the dot is flashing. Because even though cameras flash invisible, some of that flash does bleed over a little bit into the infrared. So the dot you see here is flashing. So this flasher, this is an airplane, and we can check FAA records, and we know that that's an airplane. It's so yeah. See, there you go. Flash, flash. You see how it's winking? So that's an airplane. There, that's a big flash right there. See, airplane. All right. So we have plenty of examples of that. That's what makes science part of one of the things that makes science science. Is before you claim anything, you need to have control. You need to have background. You need to have, in medical studies, it's the equivalent of, the placebo group. You have to have control. So we have plenty of examples of things like that. So now let me go back to our slide. So So what happened on Wednesday, July 14th? So if you've watched the movie A Tear in the Sky, first thing I have to explain, though, is it looks like the radiation detectors appear to start clicking more often than normal. However, in retrospect, this aspect may have been a phenomenon called pareidolia, which is where you see a pattern where there isn't none. So unlike the first event we told you about, this one is not associated with any interesting radiation. This one is a more traditional UFO event that's going to be very visual. So there are, nevertheless, even though it turned out not to be associated with radiation, this is an extremely important event. Many prominent scenes in Carolyn Corey's movie A Tear in the Sky, and rightfully so. So despite the clouds, we are still, we still found this interesting thing, which eventually did disappear behind the clouds. So now I'm going to play for you. You're going to see three different things. So we have three angles on what was the same object. We have two night vision and one visible light. Ask yourself, how often has that happened in UAP study? I would hazard to say never or almost never. So this was part of the goal of this expedition. Now, did we gain anything from having this? We don't know yet. So even though I'm bragging about the different angles and wavelengths, I do have to follow up with the caveat that we haven't finished that study to know how helpful it was to do this. Nevertheless, I'm pretty sure it's going to be helpful. Because first of all, that means it's not a camera glitch. Because why was it seen by two different people on two different night vision binoculars? They caught it on their smartphones, then through the night vision, Corbell style. And then we have also the cameraman for the movie turned his camera, I'm grateful, instead of filming them, started filming the object. Thank God. So now we know what color it is. It seemed orangish, because remember that night vision, that's false color. It interprets the data and paints it in green or in grayscale, depending on the model of and brand of the goggles. Two night vision from two different people, from Michael Hall and David Altman, and then cameraman Grant Smith, who giving credit everywhere where credit's due. That's very important. Caught it. So you're going to see. The same object three times. So let's start playing those videos. So this is not your typical, here's my one picture in UFO studies. Tell me what this is. These are three videos going on at the same time. So we're going to start playing these for you right now. Okay, so let's go here. All right. So I'm not sure if the sound is coming through. I don't think the sound probably doesn't. Yeah. Yeah. So so I'll tell you what they're saying. Look, look at that. I'm following it. So what's really great is because we have two videos, you can do very precise time stamping even without the metadata. We have, of course, the metadata on both their videos, but Dave Altman and Michael Hall, you can hear their conversations in these two videos. You can hear them say, "I got it too." And then that helps you figure out that and so you see our fuzzy glowing, our fuzzy glowing orb. By itself, this is not remarkable. By itself, this convinces no one. It's another fuzzy UFO video, except for the fact we got it in two different cameras. Two night vision, and then we have, that's not an airplane. I just showed you what an airplane looks like in the night vision. It flashes. Why? Because you have the FAA required navigation lights. It's not flashing. Okay, this is not an airplane. It could still end up being something prosaic. Definitely, but it's not your knee jerk, it's a meteor or an airplane. It's not one of those knee jerk debunkings. It's going to take some time. So they tracked it as long as they could. It eventually disappeared into the clouds. So I'm going to keep playing that for the total. So just like we're doing with all the other videos, we're going to break this up frame by frame. It's going to be more difficult to do the analysis we were talking about earlier, like with CTAP, because this was not a stationary camera. So this was them holding it, right? So we're going to have to work around the fact that, of course, it was a shaky cam. But this is still outstanding data that our team members took. So let's look at the other video. As I said, one of these was David Altman, one of these was Michael Hall. And they caught the same. They started following the same object. There it is again. So they were close to each other. So this is not. People ask, is it good for a triangulation to get size and distance? Not right off the bat. That's difficult because even though they're two different people, they're only a few feet apart, right next to each other on the island, and so that we need more angles to be able to do that. So I'll talk about in a moment how we scrambled. I know it's a car, not a jet, but we scrambled Jeremy in the Osiris to try to get a different angle from many miles away on the object to help with triangulation to determine size, shape, velocity more robustly. So because you can't do triangulation even if you have multiple viewpoints if those viewpoints are too close together. Right? You need some spread also. So this wasn't good enough yet for size, shape analysis, but you can see fuzzy, traditional UFO here, fuzzy orb, moving around, and caught by two of our team members in their night vision goggles. Very, very, very interesting. And now this is it in visible light. And you can barely see it probably on this screen, but it's an orangish fuzz, and you can see it moving around. So again, do we wish we had higher resolution of this? Of course. And that's why, we're going to have even better, but remember, this was a movie camera. This is high quality camera, okay? So of course, we're going to break this down frame by frame, zoom and continue this analysis. But right now, this is what we have in hand right now, but obviously analysis is not finished, so much more to do. You see, as usual, we do have the shaky camera issue that we're going to have to work on to determine whether this object is actually doing any anomalous motions or is it just the motion of the camera. That's going to be very difficult, of course, to disambiguate. So you can see here, this is Grant Smith, one of the cameramen on the movie A Tear in the Sky, who turned his camera up and started to catch this, which is great, so that now we have a visual light record. And we have reference points like, other lights are like stars in the sky in the area that are going to help us with the analysis, further analysis of this video. So that's what we have from that event, except that is not the end of the story for that event. There's more. But wait, there's more, right? So much later on, so months later, we found what we call the maroon saucer in the FLIR. So you'll notice the FLIR was conspicuously missing from our first event. You can't believe how badly we want to know what that hole in the sky looked like on the FLIR. And it's game over that it's a camera glitch. Why the FLIR pick it up? The FLIR was dead. Now in the movie, it seems like this is part of the woo aspect, like happens on Skinwalker Ranch, that the phenomenon shuts things off. Sadly, I wish that was the explanation. That would be more fun. There's a much more prosaic explanation. When we it just simply renamed all of our files and made it easier to look through the data, restructured the FLIR data, we were able to discover that actually FLIR went down at 10 p.m. There's a mundane explanation of just film crew probably just plugging in something extra, tripping a circuit breaker. So we're killing ourselves thinking about what would have been amazing to see that hole in the sky in the FLIR. For this event, the FLIR was active, and it's possible it caught the same object. We don't know for sure because there was only a couple frames. So I can't claim yet that this is the same object. But the timing is right. So at 9:29:08 p.m., you're going to see to the left of the cursor of something I'm going to pull up in just a couple minutes here, is we're going to play this July 14th, 21:01:11 A1 MP4 file. So we had 8 cameras. They're named A1234, B1234, all slightly different FLIR camera models. So first question, is it a camera glitch? It does not appear to behave like other known FLIR camera glitches. Remember, this is FLIR. Known camera bugs usually last 1 frame or forever, not a few frames. They're usually 100% cold, 100% hot, the max-min pixel color values. We saw those. These are cause for existence. You can also have dead pixels due to prior exposure to the sun. This does not look like any of the known glitches. By the way, we called the maroon saucer or the red saucer, but that's just refers to its temperature. It's not literally that color. So remember, FLIR is just, it's a false color image based on the heat. You're never going to find this by manually reviewing videos. You're not going to find this fast forwarding 4 to 5 times speed over our several hundred hours of video. This is why you need to combine the human sensor together with computer sensors, with the software we wrote, CTAP, because neither is perfect. The computer and a human both have advantages and disadvantages. So if you want both advantages, you have the human sensor combined. That's why, in fact, as we've mentioned earlier, why UAPx is partnering with SCU, and they're going to help us go through the rest of the FLIR data and see what other anomalies are hiding, but after it's been processed, so that instead of looking at 600 hours that would take years, the SCU is going to be looking at just a couple hours where there was actually an object. So now I'm going to show you this video, and you're going to see a human eye would never have caught this. So this was caught by actually an early iteration of CTAP, not even the first version, found this. So this is very strange, and it can still, to be fair, as I said, it can still turn out to be a FLIR glitch, a new type of one that we're not familiar with. So we do certainly have to be careful. So let's but what makes this more interesting is that, as I said, it was the same minute. We can look at the metadata, and it was within the same minute. Not the same second, but the same minute as the videos that you saw earlier from Grant Smith, David Altman, and Michael Hall. So let's take a look at that. So I'm going to play for you instead of, I do have also the full 3.5, gigabyte version, but I'm just going to play the post-CTAP version of the FLIR. And so after being run by CTAP, oh, and you can see drones, right? That's them filming us. So we catch plenty of mundane objects in the FLIR, like, a head. I think that's the back of probably Gary's head there. So we do have plenty of mundane objects. So let me fast forward, though. So at 9:29 is where something really crazy is where, so let me rewind. So you see these little circles? And so that's where, so I'm going to have to go frame by frame. Hold on. Yeah, for some reason this version doesn't have, hold on, I'm having, yeah. No, let me, I've got it, I'll find it. So, oh, I see what's going on. The fast forward on your computer goes, it goes several frames. I need to go frame by frame. Is this frame by frame here? Okay. Yeah, I'm used to doing this frame by frame. It's got to be frame by frame, or we can't get it. All right, let's try tools. All right. Yeah, this is why I use for frame by frame I use QuickTime. VLC just fast forwards too much. Actually, I'm just going to let it play, and I'm going to see if I get lucky pausing it. Yeah. So it's at 9:29:08. It's going to be at 9:29:08. So I'm just see if. No, that's a person walking by. Yeah. So let me. Yeah, there's something there in the sky. Yeah, I think that's an airplane. I'm gonna try to hit pause and get lucky. Yeah. To this. No, I didn't. Dang it.
There you go.
I'm going frame by frame now by just pausing on pausing. I'm going to get it. Because this is faster than me unplugging Kevin's computer and plugging mine in. Yeah, this is why, by the way, the video editing software, or video playing software, it sucks. There's always one software that does one thing and another that does another. Okay. How? How do I know? All right. Got it. Got it. You can see in the green circle. So it's there for a few frames, but I'm not going to risk messing it up again and showing you. It's there for only a couple frames. But there's this strange reddish thing that doesn't look like the known FLIR camera glitches that we've calibrated. So it could still end up being a new kind of glitch, but this is very interesting that 9:29, that's the same minute as that orb disappears in the clouds over Catalina, and then we see this in the FLIR. We don't have anything in the UFODAP, but we do have this in the FLIR. So you see, what a CTAP was able to pull it out, and it circled it. You see that green circle. So it was able to pull that out with pixel subtraction. It flashes by in a couple frames. Okay, you're not going to catch that by manual review of the FLIR by eye. It caught it despite it being a cloudy night, because that's how smart the software is it doesn't trigger on the clouds moving like that whole shifting. It does sometimes, like you saw me when I played the video. It's not perfect. Sometimes it got stuck on a cloud in the lower left because it was a very, very cloudy evening. So we were very lucky to have seen anything. But you can see this strange object in the left. If it is an object. So what's really strange is also the color doesn't match one on the color scale, which would imply it's a glitch. But again, an interesting glitch that's at the same time as what we saw on the island, and what the island team saw. So let me go back now to our slideshow. You think that's the end of the story? That's all that happened with that object Wednesday night? Nope, it's not the end of the story. So remember how I said we scrambled Jeremy in the Osiris? Okay, it was quite an experience. I remember getting, so Jeremy actually drove me and Kevin around. I felt like I was in the real life Ecto 1, okay, from Ghostbusters, except it's an SUV and it's for aliens, not ghosts. Well, not just ghosts, right? Jeremy did go to Skinwalker with the Osiris. So Jeremy was deployed to chase, or at least find another perspective on whatever the hell that was that I just showed you. The Osiris had 2 cameras, UFODAP cameras installed, and here's what happened that was quite odd. Jeremy saw what may have been the same object, but only in one camera, not both. So we call this the semi-vampire, right? So he saw the orb. It seemed to be the same color and size and looked like what we were seeing. Now, why did he see it on one camera but not the other? So then everyone jumps to, oh, that was a fly in the lens. If it's a fly in the lens, why are Jeremy and team member Jason, why are they seeing it in the sky go over while the camera catches it? These cameras had overlapping fields of view. So, and I just said it's not an insect. We saw it in the sky, they saw it on the island, and now Jeremy's seeing this, and why was it in one camera, not the other? So that was already strange. But it gets, so you can see that in the movie. You can see those those videos. So I'm not going to play that show. It's the same thing. You see the orb again, but it's not. It's one camera, not the other. But it gets crazier. So electronic glitches. So I said earlier that the FLIR going down, we were able to after the movie debunk that as ordinary. However, electronic glitches affected the Osiris during this incident. So the internal communications Wi-Fi went down. Jeremy says this has never happened before, but that it was similar to what happens in before the Skinwalker Ranch rocket launches on the episode he was on. The car suffered a major general breakdown after the trip, right? And so that would spawn the internal joke on UAPx where we said that they, whoever they are, owe Jeremy a Tic Tac or at least a new car, right? So this is an additional dimension of weird that occurred that night. So now what I'm going to do is I'm going to turn it back over to Christopher Altman, who's here virtually, and I will be advancing the slides for him.
Thank you. So we know that UAPs have anomalous effects on electronic instruments, and not just electronic instruments, but in the past bounced from base nuclear missiles, and as well as on Jeremy's car. So we brought with us an oscilloscope and a quantum random number generator based upon a Zener diode, which is a transistor where electron tunneling is going to cause the random numbers sequence. And we wanted it as a baseline, and anticipating nothing would happen, Occam's razor. But we also brought it along just in case there's something anomalous happening, whether that be an electromagnetic surge or whether the UAP gets close enough that it's actually warping space-time in some manner. So we just brought it along because it was simple, it was easy to bring, easy to incorporate, and we brought 2 of them, and we're currently in the process of analyzing the data right now. So it's a truly random quantum number generator, not pseudo-random, and we are in the process of analyzing it together with the FLIR data, and we should have it pretty soon. Next slide.
All right, so this is back to me now. Thank you, Chris. So this is now we're going to talk about how not everything was anomalous. So something was, so for example, for the, on the last slide with Christopher, we don't know if, could we have electronic interference since we had so much equipment? Could it be, even our own cell phones that could affect something like the Zener diode? What about, we mentioned earlier the sun. So we matched up our data, all these different data sets from all these different sensors to also solar activity, as we mentioned earlier. So we were able to do this not just with the Cosmic Watch, but also with the UFODAP. So Kevin showed you an example earlier, and now I'm going to show you another one. So this is 3:39 a.m. So originally, in an original draft of the movie, we were so excited, and we have Jeremy saying, they're there one there moment, and then they're not, and we were so excited. But this turned out to be another nothing. Well, not nothing, because like Kevin said, this in itself, we'd like to publish a paper saying simultaneous detection of solar activity in the MIT Cosmic Watch and a CCD camera being disturbed by it. So we have, I'll show you this event. So let's play that video. I double-clicked it, didn't appear. Let me double-click again. Oh, it's not, there we go. So yeah, so here you go. Let me rewind this. Yeah, so because it was playing in the background. So it's another UFODAP video. And it triggers on what seems like dots. And you see it's got just like the software I wrote CTAP for infrared. The UFODAP has its own software with Ron Ulch. And what you just saw, these speckles or sparkles, but they're not real objects. Not likely, because this did seem to correspond to solar activity. So let me go back to the slideshow now. So we have to be we found but the dots you saw earlier, like the dots in the hole in the sky, didn't seem to match. It's not the same kind of behavior, and even if it was radiation, why is it all in just those pixels? Because when you do have the CCD camera affected by radiation, it's everywhere. Because CCD cameras don't focus high energy particles, they focus visible light and IR photons. So so that's what solar activity looks like. What about airplanes? I showed you one example of an airplane in the night vision. Night vision and FLIR are not identical. They're not exactly the same thing. They operate at different wavelengths. One's short wave, one's long wave infrared. So here's a great example of what an airplane looks like in the FLIR. So I've told you what does solar activity look like. How does that affect the CCD camera? How does that affect the Cosmic Watch? What do airplanes look like? So now I'm going to show you that. So we're going to go 1846, 51, 656. So 1846, 51, mundane and prosaic. All right. 1846, 51, 656. All right. Oh, that's the main one. Where's the CTAP version? Oh, I don't have this. That is the CTAP version, I think. All right, so let's take a look at this. All right, so in this one, we're going to go to 656. So, okay, no, we're good for this one. Yeah. This one's multiple frames, so we don't need this time. So let me rewind that again. So this is let me rewind this, and then you're going to see. So at 656, there. We have a pair of airplanes, actually. I don't remember if it was into LAX or into one of the other was in Orange County, one of the other airports nearby. So you have one plane taking off and one plane landing. This is outstanding, because what this means now is we have examples of mundane objects, human-made, airplane in this case, 2 of them. We're going to, with the help of SCU, who's helping us analyze all of our FLIR data, we're going to go back to the FAA records, figure out, we know the day and the time, which flight numbers were those. That's going to help us determine the size and shapes of all the other objects with math, with trigonometry. We have control data. We can find out which airplanes those were, what size were they, 747s or A320s or whatever they were, and now that's going to help us then determine the size, shape, and speed of the unknown objects in the FLIR. So this is outstanding that we have also examples of mundane objects. They weren't just a nuisance. They're helpful. They're helpful in getting us the control data that we need. So that was an example of what airplanes look like. In some cases, we spotted the same plane at the same time in different cameras. Even better. So that's going to help us then with the triangulation of the unknown objects. That's going to help us compensate for the fact that cameras were moved or disturbed. We're at least going to be able to know at certain days and times, at least where we caught these planes, the same plane in different cameras, to be able to get things like positions and angles. So here's another mundane object that's also human-made. And this is going to be audience interactive, who's going to first be able to shout out the correct answer. I got so excited when I first saw this. I was like, wow, it's below the clouds. What was this? So I'm going to play this, and I want someone to tell me what it is. So this is July 15th, 1830. So let's go to July 15th, 1830. And so here we go. So let's see, what time was this at? This was at 6:57:49. All right. So we're going to go to 6:57:49. And you can see this has all been processed by CTAP already. And so this has got, it's got all the circles. All right. So What is that? What is that? Anyone know what that is? Nope, it's not a drone. You saw a drone earlier. It's not a drone. What is that? What? I have no idea what that is. Hang glider? Nope. Not a hang glider. It's almost cartoon shaped of this object. I'm going to play it and then I'm going to pause it. There. Helicopter. Who said helicopter? You're right. Helicopter. Very good. Another example. We can go to records, though. You have to file your flight path. So that helicopter is, again, going to help us. Okay, so on July 15th at 6:57 at least, we know at least then that the camera was pointed at such and such angle, field of view. So this is going to be incredibly useful to our collaborative analysis with the SCU and with the SCU's FLIR experts and radar experts. And for classification. So for phase 2 of classifying the objects, we're going to do both the human sensor and we're going to write another module, phase 2 of CTAP, another neural network or neural network-like software that's going to be cross-checked by the human sensor of all the SCU members who help us go through this data. And so we're going to have a library of mundane objects, and we're going to also be able to, that'll be of a service for the community for FLIR, but also we're also going to be able to narrow down to objects that are truly anomalous. Like I said, I got really excited by that white splotch at first. Remember, it's not really white. White means hot. Got really excited. It's below the cloud layer. Wow, this sucker was low. Yeah, it was a copter. So this is very, very, we also, we see the moon and other things. And then my favorite is this one we caught from multiple cameras on a clear sky. So you can see the different FLIR were different. We had different models of FLIR. That's an airplane. That's not the interesting one. There's one that comes up here at 6:10. Watch this. No, that's 6:01. That's another plane landing. Sorry, not that. Nah, it's another plane landing. Let me fast forward. I think, there we go. What's that? The aliens are invading. They're parachuting down, right? So we caught a paraglider. And you can see how wonderfully the motion detection software, though follows it. We found the same paraglider, and not one, not two, but three cameras. So that's going to be immensely helpful in our later analysis now with SCU, because now that's going to help us do the geometry. There he is again, it's the same guy in the different camera. And so this is going to help us do the self-skepticism and the self-debunking to be able to classify mundane objects. So yeah, I won't play the third one. You get the point. We saw that one in 3 different cameras. That's incredibly useful. Incredibly useful, because now that's going to help us eliminate IFOs or IAP and get down to the real UFOs, UAP. Anyone know what that famous splotch is? Can someone shout it out? What is that? What is that object on the left? The moon. Yes, who said the moon? You're right. You're right. That's the moon. So at one point we thought, well, there was a UAP hanging over my head in the camera watching. It's the moon. But this, however, is an opportunity we're going to take to show you that that's the old FLIR. Here's an example from one of the new FLIR cameras we have on UAPx. You can tell it's a crescent shape. Instead of blob-shaped, airplanes now have wings. Even a distant airplane is plane-shaped now. And that's very important because, a white cylinder looks like a tic-tac. Yeah, unfortunately, that's usually a human airplane. No longer are the airplanes just a fuzzy ellipsoid that could be mistaken for something strange. That is an international flight. That is very high up. I got that at UAlbany campus with our new FLIR that I bought myself a few years ago to do other things with, and then I realized months after the expedition, I'm like, wait a second, what about that like more advanced FLIR I had back in my lab. And so and that's not even the best example. This is miniature FLIR. Things have gotten smaller, connected to my iPhone, and my hand was shaking. So that's not even the best example of an airplane. And in fact, I have one of our new FLIR with us today. And I'm going to plug it in to my iPhone, and I'm going to take a picture of all of you. I'll do that during the Q&A so that it's more efficient while Kevin's answering one of the questions. So this is one of our new FLIR that is much smaller than what we had on the expedition, but it's 1080p instead of 360. It's better resolution. And so we were worried, though, but what's the range of this? Surely it's not going to be as good as some of the other FLIR, except I just showed you an airplane. Okay, that was tens of thousands of feet away from me. That was not during takeoff. That was not during landing. So we are ready for the future. So what are the lessons learned? First, we have to move about more cautiously within Hollywood. It was necessary to pay for the expedition. But I think in the future, if we do TV or movies in the future, it's got to be more fly-on-the-wall style. Another lesson learned, we must synchronize our clocks. We had at best 1 minute resolution, not seconds. Christopher was explaining this earlier. We need sub-second resolution, or at least 1 second. Because some of these things, it would have been nice to say, like in the UFODAP videos, we have, the cosmic watch, the radiation was a minute earlier or later. We can't prove that was the same time because we didn't properly synchronize. Things had to move around also to film scenes. We must record the exact angles and positions of all the cameras. We have to have battery backup also for all the cameras. They know that from Skinwalker, for example. These are lessons we have to apply to future expeditions. We got lucky this time, though. And we caught stuff. Not only did we catch interesting stuff, but we caught the same airplane, helicopter, in multiple cameras that's going to help us retroactively figure out the angles and positions of the cameras on the roof. So what's another lesson we learned? Is the UFO community is unfortunately extremely toxic, because even with scientists, because someone out there wants to be the first one to say they figured out what UFOs are. My own field of dark matter is very similar. We need we need continuous video recording. So we don't have more frames of the hole in the sky or the dots. We don't know how the dots disappeared. We don't know what ultimately happened to them because we didn't have continuous visible light recording. The UFODAP, which is a wonderful system, like I said, I've praised Ron many times, but we need to couple it with other and also more cameras and different systems. The UFODAP had short clips, pre-trigger and post-trigger, and so we missed some stuff. We want to have more equipment, magnetometers, tri-field meters, even just simple compasses in case the tri-field meters fail. We have magnetometer data for the UFODAP. No, we disappeared. It was not recorded. We don't know why. Software glitch. We don't have the magnetometer data that comes with the UFODAP. So we need greater redundancy. So we need we need to look at things like gravitational data as well. So future work. So Rich was just telling me you have only a few minutes left, but that's perfect because we're on the last couple slides. So we're wrapping up. We timed it perfectly. Although, like I said earlier, we could talk to you for 10 hours of our anomalies. To keep to the time, we only focus on our top two. Future work. Ultraviolet equipment. We have inherited equipment from a UAlbany professor who retired from Atmospheric Sciences Department. I don't know how he feels about UFOs, so I'm not naming him because I don't want, there's still stigma. Although he's retired, probably doesn't care, but I want to be respectful. He used this equipment to photograph lightning in slow motion in the ultraviolet. Imagine what this could do for UAP studies. It's the opposite side from infrared. We can also do better radiation detection, directionality, what type. We're working also with UFODAP with Ron Olch, trying to develop our own UAPx branded sensors, but at the same time not reinvent the wheel, and instead try to work with sensors, people who already have sensor platforms, to tweak what they have with adding our ideas to their existing ideas. So we're trying to develop what we call the Druid system. Jeremy's the acronym genius. I don't even remember what it's. But the idea with the Druid is to couple the UFODAP with FLIR, and Kevin's going to be working on this to be able to have the FLIR and the Cosmic Watch and the other sensors pointing at the same direction the camera swivels. So we're working with Ron Olch and UFODAP to be able to take something like UFODAP and add to it. So the Druid is not a brand new sensor we're going to develop from scratch. It's going to be working with people who've already solved these problems, working with them to enhance their existing sensor platforms. So we also want to add spectroscopy, like they've been doing in Norway to study the Hesdalen lights. Add spectroscopy, add gratings, passive radar system. But the most important future work is skeptical but open-minded peer reviews of our papers that we want to publish on these findings. So the documentary on our expedition came out May 3rd. Here's the IMDb entry. It's available on Amazon, iTunes, Vudu. Strongly recommend that you go get it. So here are our conclusions. So we're wrapping up now and we're heading into Q&A. We're not standing here to tell you we found definitive proof of everything. We don't have a smoking gun. I mean, I wish we did. But we don't have an alien waving from a window of the mothership. That's not what we have. But what we have are ambiguities, not even necessarily anomalies, because some of them will turn out to be statistical aberrations, but still normal. What we've demonstrated, again, I should have added, we should have put the word again here. I think this has already been demonstrated, but the phenomenon appears to be real and interesting. It's worthy of scientific study. It's worthy of the attention of PhD scientists and engineers, and it's perhaps not even that rare. Because how could we have been that lucky? Kevin and I were very concerned at the beginning of the expedition, that we wouldn't find anything. And we were so afraid that that was going to happen. We're thinking, if UAP are rare, what are the odds that, on our first try we're going to see something? Not only do you see one thing or two things, but 10 more things I don't have time to tell you about. So we found all this stuff on the first try. And so, but the other thing is, this could still turn out to be something like an unknown atmospheric phenomenon that we discovered. It's not related to non-human intelligence. But that's okay too. Even this, and also, maybe we have mistakes and some of these things are camera glitches. Great, we'll be the first to admit that. So every critic who says, UAPx, that's a glitch and that is, sure, great, maybe you're right. Guess what? And we'll explore that possibility. We already had a round table after the movie where we got around on Jeremy McGowan's channel and we said, oh, by the way, guys, like the FLIR going down, that wasn't mysterious. We explained that. So we already doing that. Is the self-skepticism and the self-debunking. Better to do it to ourselves first before other people come and say that. So those who claim, though, that scientists never make mistakes are full of it. They're being disingenuous. People say, oh, we're not going to repeat the same mistakes as UAPx. No, you'll make different ones, okay? We're all human beings, all right? So we're not robots or Vulcans. And so that's why we are trying to go through the skeptical explanation. Are the dots camera noise? Are they reflections? We are going through and not just doing truth by proclamation, but truth by mathematics. Is it thermal noise? We can test that. Are those dots in our most interesting event reflections? We can test that. So even if this all turns out to be nonsense, maybe, in the movie trailer, in the movies, the hole in the sky was called a wormhole-like anomaly. It's probably not what it is, but if it isn't, but we inspire the next generation to build wormholes and warp drives, even if there's no such thing as aliens, but we thought they were there and we thought these had these technology that inspires us to do it, then that's still something important, is making breakthrough propulsion technology a reality for humanity. So no matter what happens, we're not wasting our time here, we're doing something important. And so with that, we'll conclude and we'll happy to take your questions.
Yeah, okay, we can close that, I guess. Yeah. Just want to point out, Matthew, that I wish you would get a little bit more passion behind what he says. You know, you can hear the passion in his voice and certainly his presentation, and it's energetic, which will keep you attuned and attentive to everything that comes out of his mouth. And by the way, I appreciate also what Kevin says, every word that comes out of his mouth. I just want to point that out. I am deeply thrilled with having both of these gentlemen, as well as Christopher Altman out there in the virtual world.
Thank you.
We have a lot of questions, which is I'm going to take full advantage of. This is way more than 15 minutes we have, so I hope you're okay with that. We are actually scheduled for a lunch at 11:30, so if you take a look at your clock here, we have at least 35 minutes, so I might be able to get through the 1,000 questions that we have from everybody about what you've done. And I'm going to try and do my best to go back and forth between the virtual questions as well as the ones that are in-house. What is the assessment of the apparent random, rapid, irregular movement displayed at times of UAPs? Anybody want to tackle that? Go ahead.
Well, that's difficult for us to assess because we haven't observed that definitively, so I'm not sure I can really say anything to that. So I didn't handle the question, apparently. Do you have anything you want to add?
No.
No?
Actually, hold on. I think I can do this, and you can hold on to the mic. How's that? Good. Somebody out there said, David Mason is no longer a member of UAPx. He provided most of the equipment used for the Catalina trip. Have you managed to replace the equipment, and how has that been funded?
You'll notice our most interesting event was captured by the UFODAP. That's Ron Ultra's. Cosmic Watch was from MIT. So while the FLIR was incredibly useful, we now have a new FLIR. I'm trying to take a picture of the audience. We have both the same style FLIR that we had before that Kevin has purchased with his own funds. Obviously, we want funding to replace equipment. But more important than equipment is, as I said, is intellect. I'm sad that David's no longer with us, not because of the equipment he brought that makes nice photos, but because of his brain. We have equipment, and finally it's working. I'm going to take a photo of the audience, and then at the end of the Q&A, if Rich allows it, I'm going to put the computer back in, and I'll have a FLIR image of all of you, and you'll see how new FLIR looks. And it's amazing. This is a much newer FLIR. Of course, when I try to take the image, then there's 50 questions. Oh, do you allow the app to use, use your location or whatever? I'm like, so yeah, I hope that answers the question.
Thank you. When is your next expedition, and where, and what lessons have you learned from the Catalina investigation? Well,
Oh, that's a great question, and that's a question we'd like to answer. We are still working on planning another trip. We are still trying to procure funds. This costs money, unfortunately. If anyone wants to donate to UAPx, please feel free. You could do so on the UAPx website. We would like to go back to Catalina, of course. We had some apparent success there so far, and it looks promising, and we'd like to see more. So that's certainly a good place. We've also had suggestions from others, and we're certainly considering those as well. So,
will the team also investigate USOs? If yes, will that be achieved?
I would love to investigate USOs. I'm not sure how. That's the big question. We didn't show images of. We did get FLIR imagery of objects apparently dropping into the ocean, and like it was mentioned on one of the slides, I'm working with Sarah Little to try to procure infrasound data that's recorded from hydrophones in the channel. So that we can maybe hear them dropping into the ocean, correlate them with the FLIR images to maybe rule out possible artifacts. So that's one thing we're doing that may end up involving USOs, especially if we can obtain infrasound data. Maybe we can track them underwater and locate them and see what they do when they hit the water, if that's what was happening. So there are some possibilities there.
There's also the potential for working with NOAA on sonar data too. The NOAA partnership.
Yeah, by all means. Great point. This is, I think, a recommendation. Use the atomic clock broadcast to sync all the units. You can hear it on radio or see it on the scope.
Good suggestion. Yes.
It's a good suggestion. To Matt and Kevin, Please elaborate on how you are using a U detector to measure radiation. If there is an event nearby, you might miss it if it is not within the air shower?
Air shower.
Shower, thank you, before you have the use. And sample rates. Travis. Thank you, Travis.
It was the Greek letter mu, not u.
Mu,
muon. So
okay.
yeah, I can explain. So the cosmic watch is primarily a muon detector. However, that's like saying the human eye is a detector of red light. It also does a whole lot else. So the way we're using the cosmic watch is to not just detect muons, but neutrons, gammas, different types of particles. The reason why the primary function of the cosmic watch is a muon detector is not because it has efficiency or is tuned to that specifically, but rather that's just one of the most common particles you can see. In particle physics, we have a joke. There's like an eye chart where the muon is actually higher than visible light, and mu is like the top of the eye chart, and it's a joke about which particles are the easiest to detect. So the muon, which is the heavy sibling of the electron, is one of the most common cosmic ray particles. But a muon detector does everything else. Now the point about the shower, that's exactly why we need multiple detectors, different locations, some of the same location in coincidence to do that. In the future, we want to add directionality. We want to have a particle ID. The cosmic watch is, by the way, is a jack of all trades. I'll tell you one of the other things we're doing with it we didn't got a chance to talk about in the talk is we're also using the cosmic watch to determine what things are made of. Material analysis. You might be wondering, what does that have to do with radiation? Does that mean, are we checking for things that are radioactive? No. We're going to use what's called neutron activation analysis. You make something temporarily radioactive on purpose to determine what isotopes are in there. Think about how important that could be for, alleged crash parts. So that's the kind of things we're doing with the cosmic watch. We're using it beyond what it was supposed to be used for. We're using it as a Swiss Army knife tool beyond just its original intent of muon detection.
Can you please explain the significance of the quantum number random generator that you mentioned?
That one's for Christopher.
Christopher.
Yeah, as we already mentioned, it was to establish a baseline, and also just on the off chance that there was some kind of space-time anomaly occurring for these UAPs. But of course, Occam's razor being that it would just be a baseline for us. But we've seen electromagnetic effects. We've seen all kinds of effects for UAPs in the past, and there's the question whether or not the quantum generator would also be affected, just like these other electromagnetic and electronic.
Thank you. The orb-type UAP objects often seem to emit large flashes of light. Have you considered that this may be a form of communication, but perhaps it's not meant for us?
Yes, absolutely. We've considered it. It's a form of communication, and that's one of the reasons why we had the. David Mason had the night vision goggles that convert light into sound and can try to project back. We did not have a direct example to use that though in the expedition. So the fuzzy orb we saw was not flashing, but that thought has absolutely crossed our minds. And some of the things we wanted to do, and maybe we will try again in the future, is that if there's flashing, that we would try to project the flashing back. Historically, there are examples of this, like the case of Dorothy Izot, who communicated, I probably mispronounced her name, and communicated, I think, with flashlights. I'm sure you know the case I'm talking about. So it absolutely has crossed our minds. Is it not for us? That's absolutely possible. People always talk about other species that may be intelligent, chimpanzees, whales, octopuses. Whales always come up because of the connection to the ocean. So absolutely that's crossed our mind, and that's going to be something on our minds on future expeditions.
Thank you. There's a question here about, probably relates to the Skinwalker. The Osiris failed to work at the Skinwalker whilst on camera. Did it work when off camera, and did anything get picked up? No. Okay, the answer is no from Travis in the back. Thank you. Could RF radio frequency spikes relate more to the portal phenomena, and gamma spikes relate to propulsion of UAPs?
We have no idea. But it's a very good question. that depends on if, remember, it is very speculative to call what we found wormhole-like. We were very careful on our language because if it is a wormhole, we need a lot more evidence. It could still be something mundane in the camera or in the atmosphere. We don't know, even though we do have tools like Einstein's theory of general relativity, we don't know 100% for sure what either of those things look like, either wormholes or space-time warping. They're very speculative. But I do think that's a great idea, and I think that the spirit of that question is very good, which is that how we need unique signatures to be able to classify different types of phenomena. So that's something we do want to absolutely want to explore in the future.
There's a recommendation for your next location, by the way. Will you try high-speed camera filming in Spain? Some friends are filming high-speed moving objects at daytime near Portugal.
Yeah, just so contact us. We need funding for travel, and we need funding for more equipment. We do have some equipment, including new equipment, as I said, but the thing is, it boils down to money and also time. Because like Colonel Alexander says in his book, one of the things you need is a day job. And so we do have our day job. I look for dark matter. Kevin looks for exoplanets. Also does, has got his influence net theory, and he's got quantum foundations. We have day jobs, and so we want to absolutely do more expeditions. So we have to grow the team, though, and be able to do more expeditions in the future. But also, we have mountains of data from just the one expedition. Even if we ended up doing no more expeditions, which obviously is not going to happen, we're going to do more expeditions. We have a lifetime of data just from one expedition. So we also need help on analyzing data as we get it. But we would love to go to new locations, especially hotspots where things are being seen on a regular basis. Spain, you just mentioned, we want to go back to Catalina and reproduce, find that darn hole a second time. We want to go to Puerto Rico. There's Aguadilla. We have lots of different places that we want to go. We've got to get the money and the time to do it. But it's definitely at the forefront of our minds.
This says on CTAP, how much training data for the naive Bayes and neural net? Was that the source for training data, and did you hand mark your collected data?
Hand mark? Which mark? Which mark? Who's mark?
Did you hand mark your collected?
Hand mark. Oh, yes, we did. Yes, no, on the training, yes, that's an excellent question. The problem with most neural network training is it picks up on the wrong things. I'll give you an example of this. Is the military at one point had this neural network system to tell, is there a tank hiding in this image? They thought it was working, but then it turns out that all the neural network was doing was picking up on the difference between different types of terrain or day and night. So you have to be extremely cautious. So in our training, what we did is we had a sample of cloudy, clear, videos where we found no objects ourselves, videos where we did, day, night, different times of day, different camera angles to make sure we didn't fall into the common pitfalls. And the other thing is we didn't have an actual neural network. I said in my slides, neural network-like. We developed what's more like a naive Bayesian classifier. It's more what I call a transparent neural network. There's no black box. You know exactly why the computer did what it did, because you can look at my C++ code and be like, oh, well, that's why it circled that object but missed that one. There's no black box. It's all completely, and we're going to, after we complete our initial analysis, all that we can't do it immediately. We believe in transparency, but just like SCU, we have to balance that. And so we are eventually, all that software is going to be open source for the community to improve, because it's not the best possible. I'm not an expert in image processing, so there will be people who are expert in that who are going to take the foundations we've laid and make it even better. So once we're done with our analysis, that software is going to be open source and hopefully will be a tool for the entire UFO community that everyone can use, merge with their own software and ideas, they don't like what I did, but maybe they like this one line of code, and take elements and merge what they've done as well.
This kind of ties in what you're talking about in terms of that collaboration and working together. There was a question that just came in. It says, are the plans for UAPx collaboration with the university in Germany to be able to share your image and pattern recognition with them and vice versa? It seems like that there's some significant overlap here between CTOP and the software that they've been working on.
Yes, we will work with anyone who wants to work with us. Absolutely. Yeah, we're very. We regret that a professor, was it Hakan
Hayal.
Yeah, that he couldn't be here in person.
Yeah.
But we'll reach out offline through virtual communications, because remember, we even mentioned him. I mentioned him in my talk.
Yes, you did.
We mentioned him in our talk because we think that his efforts in Germany are absolutely heroic and deserve to be applauded, because he's really, we're jealous that our university is not as open-minded as his. We would be happy to, collaborate to mutually improve both our software and our hardware.
We'll talk more about that. Yeah, Kevin, go ahead.
And I want to add, historically, the University at Albany, specifically our physics department, used to have an agreement with the University of Würzburg where we used to exchange students. And this now looks like this would be an excellent opportunity to reinstate an agreement like that.
Wonderful.
That would be fantastic to have our students go there, their students come here, and we could work more closely that way. So
Thank you.
I wanted to say that publicly so that
Sure.
we didn't forget to.
Yeah, no, definitely draw that connection. I'm going to take a virtual question and an in-house and combine them because they're talking about ruling out something, right? Okay, so this one's, how do you rule out black projects in your study? At the same time, have you ruled out meteorites since they contain trace elements of radioactive elements? Do you want to try and tackle that, anybody?
Absolutely. So, so the meteorites, what was the first half? So second half was radioactive
So
meteorites. Black projects.
Yeah.
No, you can't. You can't. Unfortunately, you have to take people at their word. How well does that work, right? And so you'll notice we had a slide trying to rule out black projects. But the best we could do with that is logic and trust that when the UAP task force report said it's not black project, that's not black project. But you absolutely can never fully rule that out. So that's a really good point. So I would still say it's interesting. And I would still want to know then, okay, then know the truth then. So then we stumbled upon some black project. That's still pretty cool. It may not be aliens or ball lightning or something, but no, the question asker is very fair. I'm not going to sit here and lie and say, oh yeah, you can rule out black projects with this. No, you can't. We can never rule it out. The radioactive meteorite, excellent, excellent question. Unfortunately, that have to be a pretty damn radioactive meteorite then, because it's all about flux. To be able to detect what we did, that would have to be very, very high flux. The radioisotopes in meteorites that the question asker is referring to is usually, I think, is in low concentrations. I mean, you know more astronomy than me, right? Yeah, I think those are low concentrations. You detect those when the meteorite's on the ground and you're studying the sample, breaking it up atom by atom. But also, remember our most interesting radiation event, that wasn't a meteor. That was, mysterious collection of dots in a dark, hole. But that is definitely a very fair question, and that is one of the prosaic phenomena. We forgot to list it in our slides, but when I listed black holes, cosmic rays, there are countless natural phenomena that produce radiation. That's exactly why we said in our talk, high radiation, that by itself is not interesting. You have to couple that with something interesting in the cameras, because by itself, it was a radioactive meteor, it was a cosmic ray or a black hole. By itself, even a 1 in 10,000 or 1 in 100,000 chance spike, that does happen when you have a week of data from one of these astronomical phenomena.
Sure.
But no radioactive seagulls.
Chris is saying something.
No radioactive seagulls.
Radioactive seagulls, yes, exactly. My favorite is radioactive seagulls, or cold seagulls, colder than the air, right? Yeah.
Is there any evidence from the sensors that may indicate whether or not the guidance is biologic or AI-driven?
No, I don't think we can definitively say anything about these objects or UAPs because we haven't definitively proven that we've observed a UAP. So I think that we're not at that stage yet.
I'll just add that we have to be careful, like we said in our slides. We don't have, we had a slide, Kevin had a slide on the extraterrestrial hypothesis, but it's not the only hypothesis. We could still have atmospheric phenomena. We don't have the smoking gun, not from the UAPx data. We have Nimitz and we have more data out there, but from the UAPx data, we do not have evidence or proof that we have craft controlled by an intelligence. Even if we did, I don't think these categories, binary categories, are necessarily the right way to go. Who's to say there's some advanced civilization that's both AI and organic? Why we don't need, I don't think these binary classifications are necessarily correct. You could have a hive-like intelligence also, right? Fleet of Tic Tacs could be a hive intelligence. I don't think we necessarily have a binary categorization of robot, android, AI versus biological occupant.
I think that you answered this in your presentation. I think you were dealing with long-range IR, if I remember correctly. You mentioned, right?
Both.
Long wave.
No, both. Because we had
as well?
both the FLIR and the night vision. Those
Okay.
operate on different wavelengths.
So the question is, what is the IR range that your FLIR is operated in? That's the question.
Yeah.
No, it was range and distance.
It just says what did
Okay,
your,
yeah,
what
this is-
IR range did your FLIRs operate in? Like the mid-wave is like 3 to 5 micron or something like that.
I think
And it's a,
I'm going to be mistaken. I think it was 3 to 12 microns for our FLIR, but I think, remember, we had 8 cameras. They may be slightly different models. So I'm not entirely sure. I can say qualitatively that we did have both shortwave and long wave because we did have the night vision.
Right.
So night vision is not the same as
No.
FLIR. They're often mistaken. They're similar, but they're not identical technologies. It's kind of like how, visible light isn't just the visible light color. There's red, orange, yellow, green, blue, indigo, violet. Same thing with infrared. Infrared, there's an entire set of, that doesn't exist in the Crayola crayon box, but it's a whole set of different colors that aren't visible to the human eye. So we had both long and shortwave, but I believe it was primarily long. The 8 FLIR
Okay.
cameras, yeah.
thank you. When you extracted individual frames, can you go back and easily grab the preceding and following frames?
Yes, but not entirely. So if those frames don't exist, obviously we can't grab them. So like Kevin and I were saying, so if the UFODAP had 12 frames, that's all we've got. But we can, when we have an interesting event, so for example, when we run my software CTAP on FLIR, I've designed it to try to take a few frames before and after, but it's not perfect. So I'm sure eventually, for when we work with SCU and we get down to the most interesting objects, we'll still have to go back to the raw data. Because when we've clipped the frames, well, of course, we're going to sometimes lose some of when the object first appears, but it's below threshold. So we will have to go back and re-extract preceding and following frames again.
Okay. There's 2 questions that kind of like relate to each other. One, let me read this one here. Could the dark spot have been condensation and water droplets on the lens? That's that one. And then this one, did we rule out the moisture on the lens? So I'm going to add those 2 together. Okay, so.
Yeah, no, we haven't entirely ruled that out. It's difficult to. It's a difficult situation because if the dark spot were to be condensation on the lens, then you've got almost complete evaporation within a minute. So, and actually, a large percentage of that happens within 10 video frames, which are coming at like 1/24th of a second. So, you're looking at fractions of evaporation in fractions of a second, which is hard to fathom. We're going to have to look at that more closely. That's still a possibility, and that's one of the things we're looking at. The presence of the white dots are also important, and when that black spot disappears, the white dots are still there. So we've got a good bit to figure out.
If I can add to that, it does seem, again, it's not impossible yet. And again, like we did with the FLIR cameras going down, and that turned out to not be a strange a phenomenon that morning. We're still open to the possibility of a mundane explanation. But with the water spot, I'll add to what Kevin said, how improbable this is. We were more concerned about that before we discovered the additional videos when we reorganized the UFODAP data. If it is a spot of water, why does it evaporate, then recondense and re-evaporate from the same spot? Because remember, we have 2 videos, spot disappears, and then the spot's back, and then it lightens. So you can't, because we've used this, for example, another hypothesis was a fly landed on the camera. We'll then explain the dots. Okay, let's say magically there were reflections that just happened to be pointed at where the fly was. Or maybe it's thermal noise. So a good answer we got from Ron Olch, who makes the UFODAP, is the dots could be in the dark spot because that sensor noise in the dark spot, so it's correlated dark spot. But it doesn't explain then why we have have two different videos. The dark spot disappears and reappears. So let's see. So we have some condensation that evaporates and then comes back to the same spot. Or it's a fly that leaves the camera and comes back. So the thing about these explanations is they work great if you had only one video. And only one video is shown in the movie. But we have multiple videos. And when you put the videos together, this seems to destroy these explanations. So if you only look at the video, for example, the camera turns, it looks very much like those dots are sensor noise that can't possibly be in the sky. But then the next video where they're static are like, wait a second, but they're not, now they're no longer acting like noise. So when you take individual frames or even individual videos that we have, by itself, it's just like how Mick West will take the Nimitz encounter and he can debunk the FLIR or the radar or the pilot testimony, but not when you put them together. Then it's a lot of coincidence. So it's similarly with the hole in the dots.
And I'll just add that we have not yet gone through all of the UFO DAP data. We've yet to go through all that imagery. So we may find other cases where we have spots like that, maybe in different places, and we can use that to better learn what's going on. So we still have a lot of work to do.
What were the other sensors that detected the image?
Is this the hole in the sky? I'm going to assume that's what it is.
Let's go with that.
No, unfortunately, because I said the FLIR was down. We would have loved to have the FLIR to be able to see what that was, as well as a second camera like the UFO DAP, because then that rules out completely. It's not a camera glitch because the other camera saw it. It's not condensation or a fly. So unfortunately, for our one most interesting event, we don't have multiple cameras. But you'll notice for the second most interesting event, we did. We had 2 night vision, and then we had the visible light. So unfortunately, for the hole in the sky, if that's what the question asker meant, we don't have anything besides the cosmic watch radiation detector, and even there, we can't prove that particle came from that direction, and we have just the UFO DAP videos. We would love to have had more, but again, that's one of those things, lesson learned on future expeditions, greater redundancy, especially in the visible light camera.
Did we rule out any contrast changes that are consistent with reflection and motion?
We've studied that. I would not jump to saying ruled out, but we've studied that. Like, is it a contrast change because the camera is in a very low, it's a low light situation, high noise. Remember, it's like 4 a.m., so it's in its night vision mode. However, this was not a digital change, so we didn't have time to get into it. We have a graph, it wasn't in our slides, where we studied the possibility of, is it a digital change in contrast? It's not. We talked to Ron Ulch. We're also going to contact the actual camera manufacturer. In addition, you had Kevin's correlation analysis. If it was, for example, camera contrast resetting, why only around that area? So we're not finished with that analysis, but what we know so far is that explanation appears to be an unlikely one. That doesn't mean it's impossible. We're still studying it. But from the quantitative, not just, again, truth by proclamation, from our quantitative analyses that we've done, that seems an unlikely explanation so far. But we're going to keep pounding away at that, including talking more with Ronald Ulch about it. I hope he's on the line, hopefully, or listening.
I believe he is. In the Tear in the Sky film, there was a triangulation point that coincided with the ocean floor feature. Can you discuss any of that? There was like a...
I know what they're talking about.
You know what I'm talking about, right.
There was a blacked out region or something on the Google map that was being used, and I think that was mainly coincidence, that the person who did the imagery for the film just lined them up at that point.
Are there any plans to expand your collection platforms, and will there be efforts to make these platforms into an open source network? Eventually, I would love to see design, build instructions or specifications for equipment that release to a community, with the idea that the sensor platform set up over a large geographic area connected to a central network would be able to collect a large amount of data.
Yes, we do have plans for this. We have plans to improve the sensor network. One of the things that we're working on is to make the Cosmic Watch directional, be able to be sensitive to direction. So we're going to put tungsten shielding around the Cosmic Watches and allow them to be moved along with the UFO DAP. And I've started conversations with Ron Ulch to learn how to pull the information off the UFO DAP, so when it turns the PCT camera to look at something, I want to know where that camera is looking so that I can have an array of other cameras and FLIR cameras to be able to swivel and turn to look at the object that the UFO DAP is looking at, just to ensure that everything's looking at some object of interest. I have several DLSR, digital cameras that are DSLR cameras that are that I'm planning on having different telephoto lenses on. 50 millimeters so you're wide, maybe 100 millimeters so you have some more zoom, 400 millimeters so you have a lot of zoom. Have them all on the same bank so they can swivel and look at the same objects, and then we can have replicants of each of those with different filters. So if you put on a polarizing filter, if you're in a day sky, you may be able to see lines due to the Faraday effect due to high magnetic fields around an object. If we can also put on diffraction gratings, which will give us spectral information for each of those cameras, so we can collect spectra, magnetic field information, and high quality visible images all at the same time. That's one of the things we intend to do. So there's a lot we would like to do. Unfortunately, it takes funding, so part of the answer to that question should be a reference to our donation page, I guess.
I'll also add people have to be patient with us because there's still supply chain issues between COVID-19 and then Ukraine. It's going to be really hard to get more electronics for more sensors. That being said, we do have existing sensors, but we want to add to them. I mentioned in my talk, the ultraviolet. It's again the opposite end, also from the infrared. Who knows what things we're going to discover that are invisible, maybe in infrared, invisible, and visible in ultraviolet, especially when you think about things like Doppler blue shift from exotic possible propulsion technologies. So we definitely want to. We mentioned in our talk the Druid light system. We want to eventually get to the point where, we can have a sensor platform that either we provide ourselves, or alternatively we provide instructions for the community to build their own sensor platforms to help us participate. Lots of other people though already have existing sensor platforms. So like Kevin said, we don't want to completely reinvent the wheel. We want to talk to existing people. So we want to see that if we can have add-ons to the UFO, to Ron Ultra's UFO DAP versus having a completely separate thing from scratch.
Question here is, did you use radiometric IR sensors?
I'm not sure what radiometric IR is. So again, as a physicist, I still don't know everything. So I apologize. I don't know what type of IR that is.
Have the Pierre Auger Observatory or other cosmic ray experiments detected anything like your black spot in the sky? Are they even equipped to detect such a phenomena?
They're not equipped for that because they don't have visible light. They only look at radiation, so they wouldn't be able to correlate that with a visible image.
Based on the transmedium nature of the phenomena, what is planned to potentially monitor USOs, like the Long Endurance Reconnaissance UAVs, I think, or AUVs, autonomous underwater vehicles in known oceanic hotspots such as the area monitored?
That's one of the reasons we're working to get infrasound data. This data is low-frequency sound recorded from hydrophones already placed in the ocean, and so there's an organization that collects this data to verification for the Nuclear Test Ban Treaty, and so this data is available, but you have to form a contract with them, and we're working on that right now. So with underwater infrasound data, we'd hope to be able to possibly hear these objects entering water, maybe hear them underwater, and maybe track them. That would be excellent if that were possible. It really comes down to how much they actually interact with the water as they move through water. We've seen that these things can sometimes move very fast underwater. From some accounts, I've estimated speeds up to 3,000 miles an hour underwater. And you would expect a lot of cavitation at that point, but that's not observed, kind of like how you don't observe sonic booms. So it's possible that these objects don't interact with the water very much, just like they don't seem to interact with the air. And if that's the case, then you might not pick them up with infrasound, and we'll have to do it, detect them some other way. So there's going to be a lot of learning to do as we learn more about them.
This next question kind of like relates to an idea and discussions that I've had before in the past where there needs to be a technical conference or something like that to bring all the game players in the world of technology that are out there, like the Ron Olches and the other people, right? You really need to have them all come together to discuss all their various technologies and create collaboration between everybody so they can develop partnerships, relationships, and so on. I think it's an excellent idea. I've been proposing it for a long time, and I'm hoping we can do that. This one says, are you discussing strategies and collaborating with someone who has captured these UAPs, right? You know, multiple times, and they've got devices that they've created and gone out and done and everything else, and we need to create that collaboration, right? So I think that's pretty much where we agree. I think we all agree with that. That's a given that we need to do that.
Certainly.
Do we know the refresh rate of the CCD cells?
We should, if they're talking about the UFO DAP, maybe if Ron Olch is on the line, maybe you could answer that. Because, yeah, I don't know that off the top of my head. We definitely know that's knowable if he's talking about the UFO DAP. I know that the...
Two separate cameras in the UFO DAP, so it'll be camera dependent.
So I think in the interest of time, I think I want whoever that individual was, please reach out to Ron Olch. I'm
Yes.
sure he's on Hoover because he is here attending
Yeah.
virtually, and Ron will give you the specs. He knows which camera we used. I don't want to say the wrong number.
No, I hear you.
Yeah.
We have like 1 minute until lunch, and I know we could probably go on for hours talking about this. There's a lot of questions, and I know that Matt and Kevin, you know how to get on the Hoover. There's a lot of questions on here that I'm not going to be able to get to, but if you can go in and answer them, because I know you're well aware of that Hoover thing, that you might be able to help us out with that. And there's quite a few here as well that maybe at some point you can address. This is an interesting question for Matt. Did you detect any dark matter? It's a joke.
No, but my day job experiment LZ is turned on, and it is going to have results later this year.
All right. I'd like to give these gentlemen a big round of applause, please, for their session and what they've done. Kudos, and we need more of this by all means. Thank you so much for your efforts and just great work. Just great work.
Oh, Rich, one question about the Hoover. Then if I said I would take a FLIR image of the crowd, I did, even though I got a new phone a few weeks ago, I got the FLIR to work. So if I send that to you, or maybe should I send it to Lee?
Send it to me or whatever,
Can
Lee.
you make sure that all the participants get
Yeah.
that in a global message in Hoover? Yeah, I took a FLIR picture of the, yeah. You'll send it to the whole group? Okay, all right.
Sounds good. Thank you.